Hey guys, good evening and welcome back again to your Unacademy Read English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible, visible to every one of you. Let me know quickly in the chats, everybody. Let me know quickly in the chats if all of you can hear me, if I am perfectly audible, visible to every one of you. Yes? Good evening, people. Good evening and welcome back. Good evening and welcome back. So what's up? How are you all doing? All well? I'm seeing you after long, I think, 10, 12 days. Yeah. All right, Will. So as you all must be knowing, today we are going to do one of the most amazing chapters of your chemistry, right? And the name of the chapter is nothing but the electrochemistry, from which every year almost like 3 to 4 questions are asked. Okay. And as you know, I start every single session, every single chapter from the basics, from the scratch. So today also, we shall be starting this particular electrochemistry chapter from the basics, from the scratch. If you have not studied the chapter before, does not matter. If you have studied the chapter before, does not matter, right? This particular session is going to be for everyone. All right. Whosoever is preparing for NEET 2026 or whosoever is preparing for even JEE 2026, you guys are most welcome in the today's session. Yeah. People have started asking about the duration. Well, the duration of this particular session is going to be 11-12 hours because it's a big chapter. You know it already. It's one of the biggest chapters of your chemistry. So the duration is going to be definitely some 11-12 hours for sure. But in between, I'll be keeping on giving you certain breaks as well so that you can refresh yourself. Yeah. All right. So can you let me know in the chats from which part of the country you guys are watching me from right now? I just want to know from which state you guys are from. I just want to know that first. I just want to know that first. Quick, everybody in the chats. Everybody in the chats. Quickly, people, quickly, everybody in the chats. I just want to know from which part of the country you guys are watching me from. Tamil Nadu, Telangana, Maharashtra, Delhi, AP, Haryana, Kashmir. Somebody is my Hamsai. Karnataka, okay. All right. All right. Perfect, guys, perfect. So are you ready to be with me till the end? Yeah. Because as I keep on saying, like after 1-2 hours, people like their Josh fades down, right? So let me know in the chats, first of all, are you guys ready to be with me till the end? I just want to know that first. I just want to know that first. Quick. And guys, tomorrow is Sunday. Yeah, so tomorrow you can sleep properly because tonight it's going to be a sleepless night. Okay? Tomorrow, since it's Sunday, so you guys can sleep till 11-12. Yeah? All right then, so let's get going. Let's get started with one of the most amazing chapters of your chemistry. My dear students, you know, the name of this particular chapter is your electrochemistry. Okay, electrochemistry. As I promised already, I'll be starting from the basics, from the scratch. So definitely I'll be starting exactly from the basics, exactly from the scratch, right? And at the same time, the handwritten PDF of this particular session, I'll be sharing on my Telegram. If you are not the part of my Telegram yet, be the part of the Telegram as soon as possible. The name of the Telegram channel is Wassim Bhatt Chemistry Official. WASSIM BHAT Chemistry Official is the name of the Telegram channel on which I shall share the handwritten PDF, my dear students. Okay. All right. Should we start? Yes, Masroof, you can also watch it. All right, guys. So before starting this particular electrochemistry chapter, there are few basic things which I would want to share with you first of all. And what are those basic things exactly? The first basic thing, my dear students, which all of you must be familiar with, what is that? That is called as oxidation. That's called as oxidation, one of the basic stuffs from which I'm starting the chapter. And how do we exactly define the term oxidation? My dear students, oxidation is nothing but, it is defined as the loss of electrons. Oxidation is defined as the loss of electrons. Whenever you see an element losing electrons, understand that element is undergoing oxidation at that point of time. So whenever an element would be losing the electrons, since loss of electrons is called as oxidation, that means that particular element which is losing the electrons, that particular element is undergoing oxidation, as simple as that. So loss of electrons is what we call as oxidation. Similarly, my dear students, if you ask me what is reduction exactly? The simplest answer that I'm going to give you, reduction involves the gain of electrons. So whenever you see any species gaining the electrons, understand that particular species would be undergoing reduction. So in short, in simple words, loss of electrons is what we call as oxidation. Gain of electrons is what we call as the reduction. Okay. For example, my dear students, imagine that you are taking, let's say, an element X. Okay. Let's assume that this X loses one electron and is getting converted into X positive. Let's say this X loses one electron and gets converted into X positive. So I would say, in short, this X is losing the electron. And that particular species which loses the electrons, we say that particular species undergoes oxidation. Or you can see just one more thing. If I ask you, what is the charge on this X here? You'll say 0. If I ask you, what is the charge on this X here? Your answer will be +1. So if I ask you, is the oxidation state of X increasing or decreasing? I would say the oxidation state of X is increasing from 0 to +1. Remember, my dear students, increase in the oxidation state of an element is also termed as oxidation. So whenever you see an element whose oxidation state would be increasing, remember that particular element would be undergoing oxidation. Okay? Whenever you see an element whose oxidation state would be increasing, remember that particular element would be undergoing oxidation and that would be definitely losing the electrons. Okay? In the similar way, my dear students, for example, I'm taking an element Y. Let's say it's gaining one electron. And after gaining one electron, it gets converted into Y negative. Okay? So, first of all, gain of electrons is what you call as reduction. So, this Y is undergoing reduction here. Or in other words, if you want to see, if I ask you what is the charge on this y here, your answer will be 0. What is the charge on this y here? The answer will be -1. So is the oxidation state of y increasing or decreasing? I would say the oxidation state of y is decreasing, right? And let me tell you, my dear students, decrease in the oxidation state of an element. Let me write it completely. Decrease in the oxidation state of an element is termed as what? You call it as the reduction. So two simple terminologies which I would want every one of you to remember from now onwards. Point number 1, whenever you see an element undergoing increase in the oxidation state, remember that element is undergoing oxidation. That means that element would be losing the electrons. And whenever you see an element whose oxidation state would be decreasing, remember, decrease in the oxidation state of an element is called as a reduction. Okay, and that element which undergoes reduction, that will be definitely gaining the electrons. Yeah, so in short, increase in the oxidation state is termed as oxidation. Decrease in the oxidation state is what we call as a reduction. Okay. Now, my dear students, two more basic terminologies which you must be familiar with. What are those? There's a term called as oxidizing agent. Or you can call it as oxidant as well. There is a term called as oxidizing agent, or you can call it as the oxidant as well. First of all, how do we define this term and how do we identify it? That is the point here. Have a look, people. Let me tell you, oxidizing agent is the species. Oxidizing agent is the species that oxidizes others. But itself undergoes reduction. That particular species which oxidizes others, but itself undergoes reduction. What do I call that as? Oxidizing agent. What is the meaning of this? You'll get the idea in some time. Before making you understand what oxidizing agent exactly is, before making you understand that, I'm going to write the definition of reducing agent first. Reducing agent, or you can call it as the reductant as well. Now, what is the reducing agent? What is the reductant? I would say that particular species. I would say the species that reduces others. But itself undergoes oxidation. That particular species which reduces others, but itself undergoes oxidation, we call that as the reducing agent. Now, let's try to understand this oxidizing and reducing agent a bit more in detail. Try to understand, people, what I'm going to say. For example, I'm taking a general common reaction. The reaction is something like this. Zinc solid plus copper dye positive aqueous. Let's say it gives zinc dye positive aqueous, and for example, it gives copper solid. This is the reaction, for example. Okay, this is the reaction. Imagine that I need to check which one is oxidizing agent here and which one is reducing agent. Try to understand carefully what I'm going to say. First of all, if I ask you, what is the charge on the zinc here? Your answer will be 0. Charge on copper is +2. Charge on zinc is +2. Charge on copper here is 0. Now, if I ask you, is the oxidation state of zinc increasing or decreasing? 0 to +2 means increase in the oxidation state. Increase in the oxidation state is what you call as oxidation. So I would say the zinc is undergoing oxidation here. So the zinc would be losing the electrons. If this zinc undergoes oxidation here, so this zinc is basically losing the electrons. And as I told you a few minutes back, that species which undergoes oxidation, that is what you call as the reducing agent. That species which undergoes oxidation, that's what we call as the reducing agent. As simple as that. In the similar way, people, is the oxidation state of copper increasing or decreasing? +2 to 0, decreasing. And you know, decrease in the oxidation state is what we call as? Decrease in the oxidation state is what we call as reduction. A reduction involves what? gain of electrons. So I would say this copper dye positive would be gaining the electrons. And my dear students, that particular species which undergoes reduction is what you call as the oxidizing agent. So my dear students, this is the way by means of which we can check whether the species is the oxidizing agent or the reducing agent. As simple as that. Okay? Now people, let me take one more example which will make things a bit more clear to you. For example, I'm taking a reaction like this. H2 gas plus copper dye positive aqueous. Let's say it gives 2 times H positive aqueous. And for example, here I'm writing copper solid. I'm taking one general reaction here. Okay. Now, my dear students, I have to check which one is oxidizing agent, which one is reducing agent. Again, I'm going to use the same process. If I ask you what is the oxidation state of hydrogen here, it is 0. Oxidation state of copper here is +2. Oxidation state of hydrogen here, +1. Oxidation state of copper here, that is 0. Okay. So, is the oxidation state of hydrogen increasing or decreasing? Increasing. Increase in the oxidation state is what you call as oxidation. So I would say this H2 is undergoing oxidation, therefore it must be the reducing agent. +2 to 0, decrease in the oxidation state. Decrease in the oxidation state is what you call as reduction, and that particular species which undergoes reduction is nothing but that is the oxidizing agent. So this is how you identify the oxidizing agent and the reducing agent in a particular reaction. If I'm clear, let me know once in the chats quickly. If you understood the concept, let me know quickly in the chats. Yeah? So in short, increase in the oxidation state is called as oxidation. Decrease in the oxidation state is called as a reduction. That species which undergoes oxidation is called as a reducing agent. That species which undergoes a reduction is called as the oxidizing agent. As simple as that. Okay. Perfect, guys. Let's move on and let's talk about few more things. Okay. Let me take a reaction here like this. For example, I'm writing a reaction MnO4 negative plus Fe dye positive. Let's say it gives Mn dye positive plus Fe tri positive. This is, for example, a reaction which I've written. And I want you guys to check. Which one is the oxidizing agent and which one is the reducing agent. My dear students, what is the first thing you'll be doing? Understand. You'll be calculating the oxidation state of manganese here. So let the oxidation state of manganese be X. Oxygen shows -2 oxidation state. There are in total 4 oxygen atoms. The net charge here is -1. So X value when you solve, it will come out to be +7. So this manganese is basically in +7 oxidation state. This iron here is in +2 oxidation state. This manganese here is in +2 oxidation state. And this iron here is in +3 oxidation state. Now, if you look exactly what is happening, manganese +7 to +2, decrease in the oxidation state. Decrease in the oxidation state is what you call as a reduction. So I would say this MnO4 negative here, it is undergoing reduction. And that particular species which undergoes a reduction, that is nothing but your oxidizing agent. Now similarly, +2 to +3, increase in the oxidation state. Increase in the oxidation state is what you call as oxidation. So this Fe dye positive is undergoing oxidation. So it must be your reducing agent. So my dear students, this is how you guys are going to identify your oxidizing agent and the reducing agent in a chemical reaction. I believe I'm clear. Okay. I believe I'm clear. Now, let's move on. Let's move on basically to the first topic of our chapter. What is that? That is your electrochemical cell. That is your electrochemical cell. How do we exactly define the electrochemical cell? My dear students, electrochemical cell is nothing but it's a device. It is basically a device that converts. It is the device that converts, I would say, either chemical energy, the device which converts either chemical energy into the electrical energy, or vice versa. So that particular device, that particular cell, which converts either chemical energy into the electrical energy or electrical energy into the chemical energy, you'll be calling that particular device as the electrochemical cell. And my dear students, this electrochemical cell is actually of two types. One is called as galvanic, or you call it as the voltaic cell. This is the first type of your electrochemical cell, galvanic or voltaic cell. And the second one that we have to discuss, that's going to be your electrolytic cell. That's going to be your electrolytic cell. Now, what is the difference between the two cells? First of all, both these cells are basically the types of electrochemical cell. Electrochemical cell is nothing but, it is the device that converts either chemical into electrical or electrical into chemical, right? Now, this electrochemical cell I'm classifying into two types. One is going to be your galvanic, or you call it as a voltaic cell, and the second one is going to be your electrolytic cell, okay? Now, what is the difference between these two? My dear students, small differences which you are going to note right now, note right now, and with time, I'm going to explain those things one by one when I'll be teaching these two cells in very much depth, okay? So first few points I would want you guys to write, okay? And when I'll be teaching these two cells in detail, there you'll understand the exact meaning of the points, okay? See guys, galvanic cell, what does it do? It converts chemical energy into electrical energy. Galvanic cell, it converts chemical energy into electrical energy. How exactly? We'll study that in some time. Okay? Point number one. Point number two, in case of galvanic cells, spontaneous cell reactions takes place. In case of galvanic cells, when I'll be teaching you the galvanic cells, what you will see the cell reactions will be happening on its own. Cell reactions will be happening on its own, right? And that particular process which happens on its own, right? What do you call that particular process? Spontaneous process. So basically, in case of galvanic cells, when I'll be teaching you in some time, right? In case of galvanic cells, you'll observe one thing. You'll observe the cell reactions will be taking place on its own, right? So basically, the cell reactions are spontaneous. And that particular process which is spontaneous, you must be knowing it's delta G for the system at constant pressure temperature. That is negative. So in case of your galvanic cells, right, wherein spontaneous cell reactions takes place, their delta G is going to be negative. And my dear students, at the same time, remember two more things. In case of galvanic cells, we are going to use two electrodes. One is called as anode and one is called as cathode. One is called as anode, one is called as cathode. The rod of the anode will be carrying negative charge and the rod of the cathode will be carrying positive charge. How this negative comes, how this positive comes, in some time you are going to understand. Remember right now, in case of your galvanic cells, you are going to use two electrodes, anode and cathode. The rod of the anode will be carrying the negative charge and the rod of the cathode will be carrying the positive charge. And one more thing, at anode, remember, always oxidation takes place, and at cathode always a reduction takes place. At anode always oxidation takes place and at cathode always a reduction takes place. Rest you already know. Oxidation involves loss of electrons, reduction involves gain of electrons. Now, what happens in electrolytic cell? Again, I'll be writing few points for electrolytic cell as well, and slowly I'll be explaining them one by one here. My dear students, electrolytic cell, let me tell you, it converts electrical energy into the chemical energy. It converts electrical energy into the chemical energy. Let me tell you, cell reactions are carried out. Cell reactions are carried out with the help of a DC source. With the help of DC source. Cell reactions are carried out with the help of a DC source, which are otherwise non-spontaneous. Which are otherwise non-spontaneous. So basically, in case of your electrolytic cells, cell reactions are not going to happen on their own. We are going to make the cell reactions happen with the help of the external DC source, right? So basically, in case of electrolytic cells, the cell reactions are non-spontaneous, which are made spontaneous with the help of what? Which are made spontaneous with the help of external DC source. Again, how exactly? We'll get to know when I'll be teaching you this electrolytic cell in detail. Again, my dear students, again, if I ask you, since the cell reactions are first of all non-spontaneous, so I would say delta G will be positive. And in this cell also, I'll be using two electrodes. One is anode and one is cathode. But what is the difference here? The rod of the anode here carries positive charge. The rod of the cathode here carries a negative charge. The rest, all the things are same. At anode, oxidation is going to take place. And at cathode, a reduction is going to take place. At anode, oxidation is going to take place. And at cathode, a reduction is going to take place. Okay? DC means direct current. DC means direct current. Like your battery. Battery is a DC source. Yeah? I believe things are clear till here. Okay, so these are the two types of electrochemical cells. One is called as your galvanic cell or voltaic cell, and the second one is called as electrolytic cell. Now, my dear students, the first topic that we are going to discuss here, what is that? That is our galvanic cell. That is our galvanic cell. Okay, that is our galvanic cell. That is our galvanic cell. And as I told you, what does the galvanic cell do? Galvanic cell converts chemical energy into the electrical energy. It converts chemical energy into what? Into the electrical energy. Well, my dear students, the most common example, the typical example of the galvanic cell is what you call as the Daniell cell. Daniell cell, let me tell you, it is the most typical example of what? Daniell cell is the most typical example of the galvanic cell. So basically, we have to study this Daniell cell in detail. We have to study this Daniell cell in detail. And my dear students, what about Daniell cell? Let me tell you, in case of your Daniell cell, we are going to use two electrodes. One is going to be your zinc electrode. One is going to be your zinc electrode and one is going to be your copper electrode. In case of the Daniell cell, we are going to use two electrodes. One is your zinc and one is your copper. Now, my dear students, if you compare zinc with copper, let me tell you, zinc is considered to be more electropositive than copper. Zinc is considered to be more electropositive than copper. So I would say this is considered to be less electropositive than zinc. Okay. The one which is more electropositive, that would be having the tendency to lose the electrons. And the one that loses electrons, that is basically undergoing oxidation. And you know, oxidation, it takes place at anode. So I would say in case of your Daniell cell, which is the most common example of the galvanic cell, in case of your Daniell cell, your zinc electrode is going to behave like the anode, at which oxidation is going to take place. Okay? And similarly, your copper electrode. At copper electrode, remember, gain of electrons is going to take place. And you know, gain of electrons is what you call as a reduction. And reduction takes place at cathode. So there are two things, my dear students, which you have to remember here. In case of your Daniell cell, you guys are going to use two electrodes, zinc electrode and copper electrode. Zinc electrode is going to behave like the anode and copper electrode is going to behave like the cathode. Rest, you know, at anode, oxidation takes place, loss of electrons takes place. At cathode, a reduction takes place. That means gain of electrons takes place. Now, before making you understand how this Daniell cell works, you should first of all know how the zinc electrode and copper electrode is made. You should first of all know how the zinc electrode and copper electrode is made. So let me tell you that first. Let me tell you that first, my dear students. First of all, let me just do one thing. Let me take a container. This is a container. And in this particular container, I am going to take a salt of zinc. In this particular container, I'm going to take a salt of zinc. For example, in this container, imagine that I'm taking zinc sulfate. I'm taking zinc sulfate. It is the salt of zinc. And this zinc sulfate in this particular container, it would have dissociated as zinc dipositive and SO4 dinegative. So I would say in this particular container, in this particular solution, you will find zinc dipositives and SO4 dinegative. Okay. Now, if I do one thing, if I introduce a zinc rod, here in the same solution, I've introduced a zinc rod in the solution that contains zinc ions. I've introduced a rod in the solution. I've introduced a zinc rod in the solution that contains what? That contains zinc ions. Let me tell you this complete setup here. This complete setup. Zinc rod immersed in a solution containing zinc ions. This complete setup I'll be calling as zinc electrode. I'll be calling it as the zinc electrode. Similarly, my dear students, if you would want to make a copper electrode, you can do that too. So what you have to do is, you'll be taking a container. In this particular container, you are going to take a salt of copper, which is, for example, copper sulfate. You're taking a salt of copper, which is basically your copper sulfate. So this copper sulfate in the solution, it would have dissociated as copper dipositive plus SO4 dinegative. Okay. And my dear students, in this particular solution, you are introducing a copper rod. So you have introduced a copper rod in a solution containing the copper ions. You have introduced a copper rod in a solution containing its own ions, containing copper ions. So this setup also I'll be calling as the electrode. And which electrode this is? This is the copper electrode and this is the zinc electrode. And this copper electrode and zinc electrode, it is used in which cell? In case of Daniell cell. So basically, now we are going to start studying the Daniell cell exactly. So you can mark the heading here as the Daniell cell. Just mark the heading as the Daniell cell. What is the Daniell cell? First of all, it is the most typical example. It is the common example of what? It is the common example of galvanic cell, wherein chemical energy gets converted into electrical energy. Now we are going to see how this chemical energy is going to get converted into electrical energy. My dear students, understand what I'll be doing. I've taken zinc electrode and copper electrode. Let me connect these electrodes externally with the help of a voltmeter. Let me connect them externally. And at the same time, I am going to connect them internally as well with the help of an inverted U-type tube. This is the inverted U-type tube here. This is the inverted U-type tube. And my dear students, in this inverted U-type tube, what exactly I'm going to make? I'm going to keep. In this inverted U-type tube, I'm going to keep an inert electrolyte. What is the example of the inert electrolyte? You can take K2SO4. You can take NH4NO3, right? Etc. In this inverted U-type tube, you are going to take the inert electrolyte and you are going to mix it. With gelatin or agar-agar. You are going to mix this inert electrolyte with what? With gelatin or agar-agar. And when you mix the inert electrolyte with gelatin or agar-agar, what do you get? You'll be getting a jelly-like paste. And that particular jelly-like paste is introduced in this inverted U-type tube. So in this inverted U-type tube, you have got a jelly-like paste here. Okay. Now, if I first of all ask you, what all ions would be present in this inverted U-type tube? Imagine that you have kept K2SO4 here. If you have kept K2SO4 here, that means in this inverted U-type tube, there will be SO4 dinegative ions as well as K positive ions. And my dear students, the ends of this inverted U-type tube, you are going to seal it with the cotton balls. the ends of the inverted U-type tube, you are going to seal it with cotton balls. Now, this inverted U-type tube that contains an inert electrolyte mixed with gelatin, and we got a jelly-like paste which is introduced here in this inverted U-type tube. So let me tell you, this inverted U-type tube is nothing called as, it is called nothing but a salt bridge. So this inverted U-type tube here, I will be calling it as the salt bridge. Okay? I'll be calling it as the salt bridge. Now, my dear students, understand one thing. Understand one thing. As I told you already, the zinc electrode, it behaves like the anode. The copper electrode, it behaves like the cathode. Rest of the things you already know. At anode, what happens? Oxidation. Oxidation involves loss of electrons. At cathode, what happens? A reduction. And reduction involves gain of electrons. So basically, what happens exactly? At anode, oxidation is going to take place. At anode, oxidation is going to take place. And what happens exactly? What happens exactly at anode? See, this rod over here, it is made up of zinc atoms. And those zinc atoms of which a rod is made up of, those zinc atoms of which a rod is made up of, those zinc atoms will start losing electrons. They'll start getting converted into zinc dipositives, and you'll be getting the 2 electrons here. Since, if I talk about the zinc rod is made up of zinc atoms. Those zinc atoms will undergo oxidation. They will get converted into zinc dipositives and 2 electrons. Let me tell you, these 2 electrons, they'll be accumulated on the rod itself, and this zinc dipositive, it goes into the solution. It goes into the solution, due to which the solution is going to get the positive charge. Earlier, this solution was neutral. The solution was neutral because there were equal number of zinc dipositives and SO4 dinegatives present. Now, from the rod, a zinc atom is getting oxidized, getting converted into zinc dipositive and 2 electrons. Those 2 electrons are accumulated on the rod, and that extra zinc dipositive goes into the solution, due to which the solution gets positive. And since electrons are accumulated on the rod, I would say the rod is going to get the negative charge. The rod is going to get the negative charge. So, my dear students, as I had already told you, the rod of the anode, it carries what? It carries the negative charge. Now, what happens at cathode? What happens at cathode? At cathode, you know, what happens? A reduction. A reduction means what? Gain of electrons. So, what happens at cathode? Basically, these copper dipositive ions, they are basically present in the solution. These copper dipositive ions which are in the solution, they are going to collide with the rod. The copper dipositive ions in the solution, they are going to collide with the rod. Okay? Copper dipositive ions in the solution, they are going to collide with the rod. And they will take 2 electrons from the rod. They will take 2 electrons from the rod and will get converted into copper solid. And that copper solid will get deposited here on the rod. That copper solid will get deposited here on the rod. Okay? Am I clear till here, people? Quick. Everybody? So, at anode, oxidation takes place, at cathode, reduction takes place. Now, my dear students, the copper dipositives which were there in this solution, they collided with the rod. They took 2 electrons from the rod, got converted into copper solid. Now, understand one thing. Since the copper dipositive in the solution, they are colliding with the rod, taking 2 electrons from the rod. If electrons are taken out from the rod, that means this rod is going to get which charge? This rod is going to get the positive charge. This rod is going to get the positive charge, right? And initially, there were equal number of cations and anions in the solution. Initially, there were equal number of cations and anions in the solution. Now, imagine that one of the cation from the solution, it collided with the rod, took 2 electrons from the rod, got converted into copper solid, and that copper solid got deposited on the rod, due to which the number of copper dipositive ions in the solution will decrease. Due to which the number of copper dipositive ions in the solution will decrease. Earlier, there were equal number of cations and anions. Now, one of the cation collided with the rod, took 2 electrons from the rod, got converted into copper solid, and that copper solid got deposited on the rod. So, in this solution, copper dipositives, they are decreasing with time. If they are decreasing, that means the solution will be getting which charge? Negative charge effectively. Effectively, it's going to get the negative charge. Earlier, cations and anions were equal. Now, cations are decreasing. So, solution is effectively going to get the negative charge. Now, my dear students, since electrons are accumulated on this rod because of the oxidation of the zinc atoms, since electrons are accumulated on this rod because of the oxidation of zinc atoms here, right? And the path is already made. The path is already made. Can I say there will be a moment of electrons from anode to cathode? Absolutely, there will be the moment of electrons from anode to cathode. But if I ask you, is it a normal movement of electrons or this is the directional movement of electrons? I would say this is the movement of electrons in a particular direction. And you know, when charge moves in a particular direction, current is produced. So if electrons are moving from anode to cathode, if there is directional movement of electrons from anode to cathode, so definitely this cell is going to produce current. That is the use of this particular cell. That is the use of this particular cell. It converts your chemical energy into what? Into electrical energy. So the first thing which came to our mind right now, what is that? That is the direction of electrons in case of the Daniell cell is from anode to cathode. That means zinc to copper, right? And if the direction of electrons is from zinc to copper, that means anode to cathode. So the direction of current is always a reverse. Direction of current is always reverse to the direction of electrons. So I would say the direction of current is going to be from copper to zinc. This is the first conclusion, my dear students, which you have to remember. This is asked. What is the direction of electrons in case of Daniell cell? What is the direction of current in case of Daniell cell? So electrons, they move from anode to cathode. Current flows from cathode to anode. Okay. Now, my dear students, if you look carefully, what happened on this rod? From this rod, zinc atom got converted into zinc dipositive, and that zinc dipositive entered into the solution. Then again, one more zinc atom will undergo oxidation. One more zinc atom will undergo oxidation from the rod, right? So one zinc atom, it will be keeping on coming from the rod towards the solution. Due to which, what will happen to the thickness of zinc rod? Conclusion number 2. The thickness of zinc rod. The thickness of zinc rod. The thickness of zinc rod. Is it going to decrease or increase with time? The thickness of zinc rod is going to decrease with time. Or you can say, this zinc rod, it slowly dissolved in the solution. It dissolves in the solution, right? Similarly, what is happening to the thickness of this particular rod? Remember, if I talk about the copper rod thickness is going to increase with time. It is going to increase with time. Okay? It's going to increase with time. This is the conclusion number 2. My dear students, conclusion number 3. This was the reaction taking place at anode. This was the reaction taking place at cathode. If I would want to write a net reaction, let me tell you, in order to write the net reaction, the first thing which should be in your mind, what is that? In order to write the net reaction, the electrons should be balanced in both the reactions. In order to write the net reaction, the electrons, they must be balanced in both the reactions. If I ask you, are the electrons balanced here? Yes, 2 here also. Since the electrons are balanced, so you can directly add these 2 reactions. If the electrons were not balanced, then you were supposed to balance the electrons first, and then you could have added the reactions. But here, in this particular case, the electrons are balanced in both the reactions, so you can directly add these 2 reactions. And when you add these 2 reactions, you will be getting zinc solid plus copper dye positive aqueous. What does it give? It gives zinc dye positive aqueous, and with this you are getting copper solid. So this is our net reaction which is taking place in this Daniell cell. Okay, and how many electrons got cancelled? 2 electrons got cancelled. So I'll say N value is equal to 2. What does this N signify? N signifies the number of moles of electrons, exchanged between anode and cathode. The number of moles of electrons exchanged, that is represented by N, which is nothing but, that is 2. Okay, which is nothing but 2. Perfect. Am I clear with this? Am I clear with this, people? Everyone in the chats? So some conclusions which are very important. Number 1, electrons move from anode to cathode, current from cathode to anode. Zinc rod dissolves with time. The thickness of copper rod is going to increase with time, right? And N value in this particular reaction is nothing but 2. And this particular cell, what does it do? It converts your chemical energy into the electrical energy. Okay. Now, my dear students, what is the main function of this salt bridge? The salt bridge which we have used here. What is the function of it? What is the function of it? So if you exactly talk about the functions of the salt bridge, if you exactly talk about the functions of the salt bridge. Just give me a second. Let me use a different slide only. Okay. So if we talk about the functions of the salt bridge, the first function of the salt bridge, which all of you must be knowing now, what is that? It completes the internal circuit. As you saw here, the salt bridge is doing nothing but it is completing the internal circuit right here in this particular case. Now guys, point number 2, that is important. What is that? It maintains the electrical neutrality. It maintains the electrical neutrality of both the solutions. It maintains the electrical neutrality of both the solutions. How exactly? Have a look. See, as I told you, when the extra zinc ion comes into the solution gets a positive charge. When copper dye positive from the solution is reduced, the solution gets a negative charge. But remember, as soon as the positive charge enters in the solution, as soon as the extra positive charge gets developed in the solution, at the same time, from the salt bridge, SO4 dinegative will come and will neutralize it. Similarly, as soon as the negative charge is developed in the solution, at the same time, K positive is going to come from the salt bridge and will neutralize it. So what is the main function of the salt bridge? The main function of the salt bridge is that it maintains the electrical neutrality in both the solutions. It maintains the electrical neutrality in both the solutions. Okay, this is one of the important one. And the most important use of the salt bridge, what is that? Let me tell you, it avoids the liquid junction potential. It avoids the liquid junction potential. Now, what is the liquid junction potential and how the salt bridge avoids the liquid junction potential? Let's try to understand that. That's again a very important point. So my dear students, what exactly I would be doing here? Let's say I'm taking a bigger sized container like this. I'm taking a bigger sized container like this, and I'm dividing this particular container into two chambers. I'm dividing this particular container into two chambers with the help of a semi-permeable membrane. I'm dividing this container into two chambers with the help of a semi-permeable membrane. My dear students, in this left chamber, imagine that I'm keeping zinc sulfate. In this left container, I'm keeping zinc sulfate, which I believe got dissociated already into zinc dye positives and SO4 dye negatives. And the right chamber that you see here, in this right chamber, I'm taking the salt of copper. I'm taking copper sulfate in the right chamber, which already got dissociated as copper dye positive plus SO4 dye negative. Friends, if you talk about the left chamber, this left chamber contains equal number of cations and anions, due to which this left solution is electrically neutral. Similarly, this particular right solution, this solution which is on the right side, which is in the right chamber, it again contains equal number of cations and anions. So I would say this solution which is in the right chamber, it is also electrically neutral. So basically, both the solutions are right now electrically neutral. Now, what exactly am I going to do? For example, I'm introducing a zinc rod here, and here I'm introducing a copper rod. I'm introducing a zinc rod here, I'm introducing a copper rod. This is something I'll be calling as the electrode. This is also something I'll be calling as the electrode. So I have got zinc electrode and copper electrode. Now I'm connecting them externally with the help of a voltmeter. So if I ask you, is the circuit complete from outside? Yes, from the outside the circuit is complete. Is the circuit complete from inside? Inside also, as you can see, you are getting a closed loop here. You are getting a closed loop here. So the circuit is complete basically. The circuit is closed. The circuit is closed. So here, in order to close the circuit, you don't have to use a salt bridge because the circuit is already closed. You're getting a loop here. You're getting a closed loop. You're not supposed to use the salt bridge here to complete the internal circuit, as the internal circuit is already completed, because these solutions are in direct contact with the help of a semi-permeable membrane. Okay. Now, my dear students, what's going to happen? Since this is your anode, this is your cathode, and you know, at anode oxidation takes place, due to which what happens? One of the zinc atom will undergo oxidation, will get converted into zinc dipositive, and that zinc dipositive enters in this solution, due to which this solution, this left chambered solution, it is effectively going to get the positive charge. Similarly, there are copper dipositives here. They are going to collide with the copper rod, take 2 electrons from the rod, get converted into copper solid, and that copper solid gets deposited on the rod, due to which the number of copper dipositives in the solution will decrease, due to which the solution gets which charge? The solution gets a negative charge. This solution got positive, this solution got negative. They are going to attract each other, and they are going to accumulate here at the junction. They are going to attract each other, and they'll accumulate here at the junction. Similarly, due to again oxidation and reduction, these positives and negatives will keep on coming. These positives and negatives will keep on coming, and they'll keep on getting accumulated at the junction. Now, my dear students, on the left side of the junction, can I say the left part of the junction is at positive potential and the right part of the junction is at negative potential? The left part of the junction is at positive potential, the right part of the junction is at negative potential. So can I say at this junction, a potential difference is getting created? And this potential difference which is getting created here at the junction, what do you call this potential as? You call this as liquid junction potential. You call this potential difference here, which got created, as liquid junction potential. So if I do not use a salt bridge, this liquid junction potential gets created. But imagine if you had used a salt bridge. If you had used a salt bridge, what would have happened? As soon as positive charge was getting developed here in this solution, as soon as this solution was getting the positive charge, at the same time from the salt bridge, SO4 dinegative would have come, neutralized it. As soon as this negative charge got developed in this solution, at the same time, K positive would have come and neutralized this solution, due to which there would have been no positive, no negative getting developed in the solutions. If there are no positives, no negatives getting developed in the solutions, I would say this potential difference at the junction would not have got created. Okay, so I would say the main and the important function of the salt bridge is it avoids the liquid junction potential. I believe this is also clear to everyone. Now, my dear students, let's talk few things about the inert electrolyte that we use. Let's talk about few more points about the inert electrolyte that we use in the salt bridge. Let me tell you the inert electrolyte in the salt bridge. The ions of the inert electrolyte. The ions of the inert electrolyte must not participate in the net cell reaction. In the net cell reaction. My dear students, as you see, this was our net cell reaction. In this net cell reaction, do you see any K positive or SO4 dinegative? There is no K positive or SO4 dinegative in the net cell reaction. So remember, that electrolyte is used, right? That electrolyte is used as the inert electrolyte whose ions won't participate in the net cell reaction. Point number one. Point number two. The ionic mobilities of cation and anion. The ionic mobilities of cation and anion must be the same. Must be the same. What does that mean? That means the speed with which an anion from the salt bridge enters a solution, with the same speed, cation should also enter into the same solution. So their ionic mobilities, their speed must be the same. One more thing, the transportation number. What is transportation number? You'll get the idea in some time. The transportation number of cation and anion must be the same. Transportation number of the cation and anion must be the same. In short, remember one thing. What is that? The speed with which cation and anion from the salt bridge are going to enter into the solution, they must be the same. They must be the same. The speed with which cation enters into the solution and anion enters in the solution, they should enter into the solution with the same speed at the same time. Okay? Are all these things clear till here? Let me know once in the chats, quick. Let me know once in the chats, quick people, everybody. Yeah. Now there is one more very, very, very important point, which I would definitely want you guys to remember. What is that? This is the point. This is the point, guys. Just read the statement once. Just read the statement once. The statement is pretty simple, guys. What is the statement? If Ag positive ions, Hg di positive ions, Pb di positive ions, Tl helium positive ions, if they are present in any of the solutions, if they are present in any of the solutions, if they are present in any of the solutions, at that point of time, you are not going to use which inert electrolyte? You are not going to use KCl as the inert electrolyte. If any of these ions are present in the solutions, in the anodic solution or cathodic solution, if any of these ions is present, at that point of time, you guys are not going to use KCl as the inert electrolyte. Why? Because what KCl does, KCl when reacts with these ions, what's going to happen? A precipitate gets formed. Precipitate gets formed at the mouth of the salt bridge. Precipitate like AgCl, Ag2Cl2, PbCl2, TiCl, it gets formed at the mouth of the salt bridge, right? Due to which it will be really difficult for the ions to migrate into the solution. Okay? So whenever, my dear students, remember it directly as a point, whenever you have got a Daniell cell in which the ions like Ag positive, Hg di positive, Pb di positive, Tl positive are present, in that particular galvanic cell, you guys are not going to use the inert electrolyte as KCl. Why? Because this KCl, it forms precipitate with these ions that gets accumulated at the mouth of the salt bridge, due to which the migration of ions towards the solutions, right, that is going to be difficult. So remember this particular point as the memory-based point. Okay? Wassim sir, I'm preparing for JEE, but I'm doing chemistry from here. And I think this is more than enough for me. Yes, this is definitely going to be more than enough for you. Okay? Lecture plus the DPP, which I keep on sharing after the session, just solve that. That's more than sufficient. Don't worry. All right. Now, my dear students, there is one more important thing. What is that? That is the effect of external battery on the galvanic cell. Effect of external battery on the galvanic cell. What happens exactly? Let's try to understand. For example, I am taking a Daniell cell. Let's say I'm taking a Daniell cell. So this is your one of the containers that contains zinc sulfate. Okay. This is one more container. What does it contain? It contains copper sulfate. In this particular container, you are introducing a zinc rod. In this particular container, you are introducing a copper rod. So how many electrodes do I have? I've got two electrodes. One is my zinc electrode and one is my copper electrode. Let me connect these electrodes externally with the help of a voltmeter. Let me connect these electrodes internally with the help of a salt bridge. So I got a complete galvanic cell. I got a complete galvanic cell. Now, my dear students, what exactly am I doing? What this galvanic cell does? This galvanic cell produces current. This galvanic cell, it produces current. Okay, think over it logically. If this galvanic cell is producing current, that means there must be the potential difference between these electrodes due to which current is produced. You know, as per your Ohm's law, current flows due to what? Potential difference. Here in the galvanic cell, current is flowing from cathode to anode. You know that. So there must be potential difference between these two electrodes by means of which current is produced by this particular cell. So definitely between these two electrodes, there must be the potential difference. Okay. Now guys, what exactly am I going to do? Here, this rod carries a negative charge. This rod carries the positive charge because this is anode, this is cathode. Okay. Now here I'm going to take an external battery. External battery. One battery I'm taking. This is the positive end of the battery. This is the negative end. Positive end of the battery, negative end. Okay. I took a battery here. I took a battery here, people. And here, for example, I'm keeping a switch. I'm keeping a switch as well. Okay, I took a battery. Now, what exactly am I doing? I'm connecting this particular wire. I'm connecting the negatively charged rod with the positively charged plate here. And this I'm, for example, joining with the negatively charged plate. Try to understand what am I doing. I took the external battery. The positive end of the external battery is connected with the negative one. The negative end of the external battery is connected with the positive one. Now, what happens exactly? There are some conclusions which I would want you guys to remember. Okay, I'm not going to go into the details of all this, right? Because we have not discussed EMF yet. Okay, I'm not going to go into details of all this, but some important 3 conclusions I would want you guys to remember for now. What are those conclusions? Conclusion number 1. My dear students, when the voltage of the external battery was kept less than 1.1 volt, when the voltage of the external battery was kept less than 1.1 volt, at that time it was observed that the electrons were going from zinc electrode to copper electrode, and current was going from copper electrode to zinc electrode. This was the first conclusion. What this conclusion is? When the external battery voltage was kept less than 1.1 volt, current was flowing from copper to zinc. Second point. My dear students, when the voltage of the external battery was kept exactly 1.1 volt, at that time there was no current in the cell. No current was generated from the cell. That means the cell was not working at this particular point of time. The third point. When the voltage of the external battery was kept greater than 1.1 volt, everything reversed. What reversed exactly? Electrons were now flowing from copper to zinc, and current was now going from zinc to copper. That means the cell was now behaving as the electrolytic cell. It was now behaving like the electrolytic cell. These are the 3 important conclusions. They can be asked directly in the form of the memory-based thing, right? When external battery is connected with the galvanic cell with reverse polarity, what happens exactly? Okay, what happens exactly? So remember these 3 points. If I'm clear, let me know once in the chats so that I can move on. Let me know quickly in the chats so that I can move on. All clear till here? Everybody quick in the chats. All right, people. Now comes the point. What is that? That is, how do we represent a galvanic cell? How do we represent a galvanic cell? This is again one important thing. And just one thing, my dear students, I would want you guys to remember. What is that? Try to understand. In order to represent a galvanic cell, in the middle, always I'll be drawing 2 lines. In order to represent a galvanic cell, in the middle, I'll be always using 2 lines. And my dear students, on the left side, these two lines in the middle, what does it represent? It is going to represent, these 2 lines are going to represent a salt bridge. These 2 lines are going to represent a salt bridge. On the left side of the salt bridge, what do we have? We write anode. On the right side of the salt bridge, we write cathode. On the left side of the salt bridge, we write anode. On the right side of the salt bridge, we are going to write the cathode. Yeah? Sir, letters cannot be seen. I think it's all fine. I can see. Okay, so first thing, guys, These two lines are going to represent the solid bridge. On the left side of it, you are going to write the anode. On the right side of it, you are going to write the cathode. Now, how exactly? How exactly? Try to understand. For example, I have got a galvanic cell whose net reaction is like this. Zinc solid plus copper dye positive aqueous. It gives zinc dye positive aqueous. And for example, you have got copper solid. Let's say this is a net reaction which is taking place in some galvanic cell. This is a net reaction which is taking place in some galvanic cell. And after looking at this net reaction, I need to represent a cell. How exactly I'm going to represent it? Try to understand all the things what I'll be telling you. First of all, oxidation state of zinc, 0. Oxidation state of copper, +2. This zinc is in +2. This copper is in 0 oxidation state. Is the oxidation state of zinc increasing? Yes. Increase in the oxidation state is what you call as oxidation. So zinc is undergoing oxidation. Similarly, +2 to 0, decrease in the oxidation state. Decrease in the oxidation state is what you call as a reduction. And you know, oxidation takes place at anode, and your reduction, it takes place at cathode. Oxidation takes place at anode, and your reduction, it takes place at cathode. So how do I represent it exactly now? These two lines are going to represent the solid bridge. On the left side of the solid bridge, I'll be writing anode. At anode, do you see oxidation is taking place? Zinc solid is getting converted into zinc dye positive aqueous. So I would say zinc solid is getting converted into zinc dye positive aqueous. Now, if I ask you, is the phase same here or different? This is in solid phase. This is in aqueous phase. So phase is different. When phase is different, you use the term slash in between them. When the phase is different, you use this term slash. If the phase was same, then you could have used comma instead of slash. Okay. Similarly, on the right side, what do we write? On the right side, we write cathode. And at cathode, reduction takes place. Right? Reduction of what? Copper dye positive. Into what? Copper solid. So at cathode, I would say copper dye positive aqueous is getting converted into what? Copper solid. So tell me, is the phase same or different? Again, the phase is different. So use the slash in the middle. So you have represented this particular cell properly. I believe it's clear. Now, for example, let's say you have got a cell whose cell reaction is this one. You have got a cell whose cell reaction is this one. Okay? You have got a cell whose cell reaction is this one. Now, after looking at the cell reaction, I would want to represent the cell. How exactly am I going to do it? Again, oxidation of iron 0. Copper here is in +2. Here iron is in +2. Here copper is 0. Now 0 to +2 means increase in the oxidation state. Increase in the oxidation state is what you call as oxidation. And you know, oxidation takes place where? Oxidation takes place at anode. Similarly, +2 to 0, decrease in the oxidation state. Decrease in the oxidation state is what you call as a reduction. What you call as a reduction. And reduction takes place where? Exactly at cathode. Okay. Now, my dear students, these two lines in the middle, they are going to represent what? They are going to represent a solid bridge. Now, let me tell you, on the left side of the solid bridge, what do we write? We write anode. At anode, Fe solid. At anode, as you can see, Fe solid is getting converted into what? It is getting converted into Fe dye positive aqueous. Is the phase same or different? Different, so use the slash. Right? Now, similarly, on the right side, what do we have? On the right side, what do we have? On the right side, we write the cathode. And you know, at cathode, what happens? Reduction. Copper dye positive is getting converted into copper solid. Copper dye positive aqueous is getting converted into copper solid. So is the phase same or different? Again, the phase is different. So use the slash in the middle. And if the phase is same, then use comma. If the phase is different, use the slash. I believe I'm clear. Okay. Now, for example, let's say you have got the cell whose cell representation is given to me like this. Let's say you have got the cell whose cell representation is given to me like this. I mean, the net cell reaction is given to me like this. By looking at the net cell reaction, I have to represent the cell. I have to represent the cell. So again, my dear students, the similar thing I'll be doing. Oxidation state of zinc here is 0, right? Oxidation state of hydrogen here is +1. This is +2. This is 0. Now 0 to +2, increase. Increase means oxidation. And you know, oxidation takes place where? At anode. This is undergoing reduction. Okay, so this is going to be my cathode. So you identified your anode and cathode. So in the middle, two lines, salt bridge. On the left, anode, oxidation. And oxidation means your zinc solid is getting converted into what? It is getting converted into zinc dipositive aqueous. The phase is different, again slash. Now here, H positive aqueous is getting converted into what? Is getting converted into H2 gas. Phase is different, use the term slash. Till now, my dear students, whatever electrodes we made, till now, whatever electrodes you saw, everywhere it was solid aqueous. It was solid aqueous, right? For example, here in this particular case, it was solid aqueous, right? Let's say, take the second case. It was solid aqueous. It was, sorry, not this one. Where is that? Okay, here, in this particular case, it was solid aqueous. So whenever your electrodes are basically solid aqueous, whenever your electrode is like this, solid aqueous, so it's a normal electrode basically. It's a normal electrode, which is made under normal conditions. This is again a normal electrode. But whenever you have got an electrode wherein the phase is not solid aqueous, it can be gas aqueous, it can be aqueous. Wherever you see an electrode where the phase is not solid aqueous, there you will have to use platinum solid as well. Okay? Remember this particular point directly. Whenever you see an electrode wherein the phase is not solid aqueous, it is something apart from solid aqueous. It can be aqueous, it can be gas aqueous, anything, right? At that point of time, you will have to use platinum solid as well. Now, let me take one more example. With that, things will get clear. See, guys, we have got a galvanic cell whose net cell reaction is, for example, this one. Now, first of all, when you calculate the oxidation state of chromium here, it will come out to be +6. Oxidation state of iron here, +2. This chromium here is in +3. And this iron here is in +3. Now, few students must be thinking, how come the oxidation state of chromium is 6? See, let the oxidation state of chromium is X. There are 2 chromium atoms. Oxidation state of oxygen is -2. There are 7 oxygen atoms. The net charge is -2. When you solve this, the value of X will come out to be +6. Okay? Now, +6 to +3, decrease. Decrease means reduction. So this Cr2O7 dinegative is undergoing reduction. If it undergoes reduction, that means it's going to behave like the cathode. Similarly, +2 to +3, increase. Increase means oxidation. And you know, oxidation takes place where? Exactly at anode. Now, since you identified your anode and cathode, so in the middle, salt bridge. On the left side of the salt bridge, anode. At anode, oxidation is taking place. And as you can see, Fe dipositive aqueous is getting converted into what? It is getting converted into Fe tripositive aqueous. Now, if I ask you, is the phase same or different? The phase is same. So use comma in the middle, not the slash. Use comma. Now, people, tell me one more thing. Is the phase solid aqueous? No, the phase is aqueous. Whenever you see the phase, anything apart from solid aqueous, you'll be using a term platinum solid here as well. So I'm using the term platinum solid. Now on the right, cathode. At cathode, reduction. Cr2O7 dinegative gets converted into Cr tripositive. Cr2O7 dinegative gets converted into what? Cr tripositive aqueous. Now again, the phase is different. Sorry, the phase is same. So use comma in the middle. Now, it is not solid aqueous, it is aqueous. So use platinum solid. So whenever you see the electrode apart from solid aqueous, you have to use the platinum solid as well at that point of time. If I'm clear, let me know once in the chat till now. Did you understand how exactly the cells are represented? Did you understand how exactly the cells are represented? Believe yes. Perfect, guys. Now comes one more important thing. What is that? Now the point is something very, very, very important, guys, which you have to understand in detail, because the entire chapter is based on the things which I'm going to tell you now. So have a proper eye here on the screen. How to write the net cell reaction for a given cell. How to write a net cell reaction for a given cell. See, guys, try to understand carefully what I'll be saying. First of all, let's say I'm taking a cell here. The cell is like this. Zinc solid, zinc dye positive aqueous, salt bridge, copper dye positive aqueous, copper solid. Now, first of all, these two lines, they represent what? Salt bridge. You know, on the left side of the salt bridge, what do we have? We have anode. On the right side of the salt bridge, what do we have? We have cathode. Now, if I ask you what happens at anode, you know, at anode, oxidation takes place. Yeah? At anode, what happens? Oxidation takes place. At anode, oxidation takes place. Oxidation means loss of electrons. So basically, at anode, your zinc is getting converted into zinc dye positive. Your zinc is getting converted to zinc dye positive. So 0 to plus 2, 0 to plus 2, 0 to plus 2, increase in the oxidation state. Increase in the oxidation state is called as oxidation, which means loss of electrons. So I would say at anode, zinc solid would be getting converted into zinc dye positive, and with this, you'll be getting 2 electrons as well. Now similarly, what happens at cathode? At cathode, reduction takes place. See, plus 2 to 0. Plus 2 to 0. Decrease in the oxidation state, which means the reduction, gain of electrons. So I would say this copper dye positive. This copper dye positive, it would be gaining how many electrons? It would be gaining 2 electrons and then getting converted into copper solid. Now, in both the reactions, are the electrons balanced? The electrons are balanced in both the reactions. If electrons are balanced in both the reactions, just add them up. When you add them up, 2 electrons are cancelled. So the net reaction is zinc solid plus copper dye positive aqueous. It gives me zinc dye positive aqueous, and with this you'll be getting copper solid as well. So this is my net reaction. Now if I ask you how many electrons got cancelled, 2. That means the value of N here is 2. That means the value of N here is 2. Now there is one more thing, that is a reaction quotient. Reaction quotient represented by QC. Reaction quotient. Reaction quotient, which is represented by QC. Now, how do we exactly write the expression of reaction quotient? Well, my dear students, few things I would want you guys to remember here. What are those things? Whenever you see any reactant or product in aqueous phase, you are going to use the term concentration for that. Whenever you see any reactant or product in aqueous phase, you are going to use a term concentration for it. Whenever you see a reactant or product in gaseous phase, here you will be using the term pressure for it. And whenever you see any reactant or product in pure solid or pure liquid form, it is not going to be considered. It's not going to be considered. These are the 3 things which I would want you guys to remember. Now, my dear students, in order to write the expression for QC, remember, you'll be always starting from the product. You'll be always starting from the product. This product is in aqueous state. The one that's in aqueous state, what do we use? We use the term concentration. So that's the reason I wrote concentration of zinc dye positive. Raised to the power, the stoichiometric coefficient, that's 1 here, multiplied by this copper, it's in solid state, nothing to do with this, divided by, come to the reactant side. This is solid, nothing to do with this. This is aqueous, so use its concentration. concentration of copper dye positive raised by its stoichiometric coefficient. So this is how you write reaction at anode, reaction at cathode, net reaction, N value, and QC expression. I believe I'm clear with this. And people, if I'm clear with this, let me take a few more examples. With that, things will get more clear to you. For example, I'm taking a cell like this. Platinum solid, H2 gas, H positive aqueous, salt bridge, copper dye positive aqueous, copper solid. This is your cell first of all. This is your cell first of all. Yeah? Now, what all things we can conclude from the cell? These two lines represent the solid bridge. On the left, what do we have? We have anode. On the right, what do we have? We have cathode. At anode, what happens? At anode, what happens? Oxidation. At anode, what happens? Oxidation. Oxidation means loss of electrons. So basically, as you can see, at anode, H2 is getting converted into H positive. So 0 to +1. 0 to +1 means increase in the oxidation state. Increase in the oxidation state means oxidation. Oxidation means loss of electrons. So when H2 gets converted into H positive, when H2 gets converted into what? When H2 gets converted into H positive, it would be definitely losing electrons. H2 would be losing electrons. Now the point is how many? First of all, these are 2 hydrogen atoms here. I'll write 2 hydrogen atoms. Now, 0 to +1. 0 to +1. What is the change in oxidation state? 0 to +1. The change in oxidation state is 1. 1 is the change for 1 atom. I have 2. So H2 will be losing 2 electrons. And then it will be getting converted into H positives here. This is the reaction at anode. Now, cathodic reaction, all of you already know. What happens at cathode? At cathode, reduction takes place. +2 to 0. Decrease in the oxidation state means reduction, gain of electrons. So copper dye positive aqueous would be gaining 2 electrons and getting converted into copper solid. Electrons are balanced in both the reactions. So just add these reactions. When you add these two reactions, your net reaction becomes H2 gas plus copper dye positive aqueous. It gives twice H positive aqueous plus copper solid. Since 2 electrons got cancelled, so I would say N value here is 2. Now, how do I write the reaction quotient expression? I will be starting from the product. This is an aqueous state. The one that's in aqueous state, you are going to use its concentration. Concentration of H positive raised by stoichiometric coefficient 2. Solid, nothing to do with this. Divided by H2, gaseous phase. So pressure of H2 gas raised by stoichiometric coefficient 1. Aqueous, use the term concentration. Concentration of copper dye positive raised by stoichiometric coefficient 1. So this is how you guys are going to write the expression for QC for this particular reaction as well. So tell me once in the chats. So people tell me once in the chats. So people tell me once in the chats if I'm clear to everyone. Quickly. Got it? Okay. Let me take one more example. And with that, I believe things will get more clear. Let me take one more example. With that, things will get more clear. Understand, guys? For example, I'm taking a cell like this. Platinum solid. Fe dye positive aqueous. Fe tri positive aqueous. Salt bridge. MnO4 negative aqueous. Mn dye positive aqueous. And here I'm using platinum solid. This is the cell, for example. Now what do we have to do? We have to do all the stuff whatever I've taught you till now. So first of all, people, on the left side of the salt bridge, what do we have? We have anode. On the right side of the salt bridge, what do we have? We have cathode. Now, what happens at anode, first of all? I would say at anode, oxidation is going to take place. At anode, oxidation is going to take place. Oxidation means loss of electrons. See, at anode, Fe di positive gets converted into Fe tri positive. Fe di positive aqueous gets converted into what? Gets converted into Fe tri positive aqueous. So plus 2 to plus 3, the change in the oxidation state is 1. So I would say Fe di positive would be losing 1 electron, getting converted into Fe tri positive. Similarly, what will be happening at cathode? As you can see, at cathode, reduction takes place. MnO4 negative gets converted into Mn di positive. MnO4 negative, it gets converted into Mn di positive. Now, if I ask you, what would be the oxidation state of manganese here? It will be plus 7. Plus 7 to plus 2. Decrease in the oxidation state. Decrease in the oxidation state is what we call as reduction. Reduction means gain of electrons. So MnO4 negative would be gaining 5 electrons. Final minus initial. The value comes out to be 5. It will be gaining 5 electrons and then would be getting converted to Mn di positive. Right? Now, my dear students, if I ask you, are the electrons balanced in both the reactions? No, the electrons are not balanced. So what am I supposed to do? I'll be multiplying this reaction by number 5. So that this becomes 5 times, this becomes 5 times, this becomes 5 times. Now the electrons are balanced. Now you are going to add these two reactions. When you add these two reactions, my net reaction becomes 5 times Fe di positive aqueous plus MnO4 negative aqueous. It gives 5 times Fe tri positive aqueous plus Mn di positive aqueous. Now, if I ask you what is the N value here, your direct answer should be 5. N is 5. N is 5. Just give me a second, guys. There is some electricity cut. Just a second. Just be like this, okay? Let me get the generator on. Do you like the dark mode better? Do you like the dark mode better? Then I can continue like this only. If you like the dark mode better. No, I don't like it. No, I don't. Is it actually good? Okay. All right, let's move on now. Since we added the reactions and since 5 electrons got cancelled, so I said N value is nothing but 5. Now you tell me one thing. Is this reaction balanced? The reaction is not balanced. See, 4 oxygen atoms here, no oxygen atom on this side. The reaction is not balanced. Now the next thing after this is going to be, you will be balancing the oxygen atoms with the help of water molecules. You will be balancing the oxygen atoms with the help of water molecules. Okay? That is something we have to discuss in redox reaction chapter. But right now, I'm just teaching you, so remember it for now. So in order to balance oxygen, we have to add water molecule on that side which is oxygen deficient. How many oxygen atoms on this side? 4. How many oxygen atoms on this side? None. So right side is oxygen deficient. How many? 4 oxygen deficiencies. So add 4 times water molecules on this side, which is oxygen deficient. Now, try after balancing oxygen, you have to balance oxygen. Sorry, after balancing oxygen, you have to balance hydrogen. Do you see any hydrogen here? No. Do you see any hydrogen here? Yes. How many? 8. So this side is hydrogen deficient. This side is hydrogen deficient. And I'll be adding some 8 H positives on that particular side, which is hydrogen deficient. Now the reaction is balanced. Now the reaction is balanced. Now we can easily write the expression of QC. You will be starting with the product. This is an aqueous phase. So concentration of Fe, tri-positive. Raised power stoichiometric coefficient, that is 5. Mn di-positive in aqueous phase. So concentration of Mn di-positive. Raised power stoichiometric coefficient 1. This water is in liquid phase. Nothing to do with that. Divided by, come to the reactant side. This H positive, since it's an ion, ions are supposed to be in aqueous phase only, right? That's why I wrote aqueous here. Okay. So this is going to be concentration of H positive, raised power stoichiometric coefficient, that's 8. Fe di positive, it's an ion. Concentration of Fe di positive, raised power stoichiometric coefficient 5. MnO4 negative, again in aqueous phase. If it is an aqueous phase, so it's going to be concentration of MnO4 negative, raised power stoichiometric coefficient, that's 1. So this is the expression for QC, which I was supposed to calculate. This is the expression for QC, which I was supposed to calculate. Am I clear with this, everybody? Is it clear, people? Is everything clear till here? You have to balance oxygen with the help of water molecules. We did not start Nernst equation yet. Just wait. We did not start the Nernst equation yet. All right, people. So I believe things are clear till here. Now we are going to enter into the new part of the chapter. What is that? That is electrode potential. But electrode potential will be starting after a 15-minute small break, so that you can have a tea or coffee. Okay? I'll be also back on time. Okay? All right, a small break. Go have a tea and come back on time, guys, because now we are going to enter into the real phase of the chapter. See you in some time. Is everyone back? All right. Yes, Musruf, you can watch it. You can watch it. Don't worry. So tell me quickly in the chats if all the things which we have discussed till now, are they absolutely clear to you? Say it once in the chats. Say it once in the chats if all the things discussed till now are super clear to you or not. Everyone. Everyone. All right, people. So let's move on now to one more amazing topic. What is that? Something very important from which questions are frequently asked. Okay. And this is nothing but electrode potential. So first of all, how do we define the term electrode potential? Let me write its small definition and then I'll make you understand what this electrode potential is all about. My dear students, electrode potential is defined as the potential difference. It is defined as the potential difference that gets created, the potential difference that gets created between the rod and the solution. The potential difference that gets created between the rod and the solution. And let me tell you, it is represented by capital E. It is represented by capital E. Now let's try to understand what exactly it means. See guys, for example, imagine that there's a container and in this particular container, for example, I am taking, let's say, zinc sulfate. So the zinc sulfate in the container, assume that it has dissociated completely its ions. Ions are zinc dipositives and SO4 dinegatives. The zinc sulfate that has been taken in a container, that has got dissociated completely into its ions. Ions are zinc dipositives and SO4 dinegatives. So right now in the solution, there are equal number of cations and anions present. So I would say this solution right now is electrically neutral. Now people, for example, I'm introducing a zinc rod here in this container. I'm introducing a zinc rod here in this container. So can I say the zinc rod is placed in a solution containing its own ions? The zinc rod is placed in a solution containing what? Containing its own ions. So this complete setup I'll be calling as the electrode. This complete setup is called as the electrode. For example, when this electrode behaves like the anode, what happens? When this electrode behaves like the anode, oxidation takes place. Oxidation takes place. So basically, the rod is made up of zinc atoms. Those zinc atoms of which rod is made up of, those zinc atoms will undergo oxidation. And those zinc atoms will get converted into zinc dipositives. And with that, you'll be getting 2 electrons. And you know, these 2 electrons will be accumulated on the rod. And this zinc dipositive, that goes into the solution. And when the zinc dipositive goes into the solution gets the positive charge. The solution gets a positive charge. And similarly, there are electrons accumulated on the rod. I would say the rod gets the negative charge. My dear students, as you can see, the rod got negative charge, solution got positive charge. So can I say, between the rod and the solution, potential difference got created? Absolutely, between the rod and the solution, between the rod and the solution, potential difference got created. And this potential difference, which gets created between the rod and the solution, is what you call as the electrode potential. Read the definition. The potential difference that gets created between the rod and the solution is what you call as the electrode potential. Yeah. Now, my dear students, again, I'm taking the same zinc electrode. Again, I'm taking the same zinc electrode. So, for example, this is again the zinc sulfate, which got converted into zinc dye positives and SO4 dye negatives. So, there are equal number of cations and anions present right now in the container. So, the solution is right now electrically neutral. So, here you are introducing a zinc rod. Here you are introducing a zinc rod. Now, my dear students, assume that this zinc electrode now behaves like cathode. If the zinc electrode behaves like cathode, what's going to happen? A reduction is going to happen. Reduction. Reduction means gain of electrons. Reduction means gain of electrons. So in this solution, you have got zinc dye positive ions. These zinc dye positive ions, which are there in the solution, they are going to collide with the rod. They are going to take 2 electrons from the rod. So the zinc dye positive ions in the solution, they are going to collide with the rod. They are going to take 2 electrons from the rod and will get converted into zinc solid. So the zinc dye positive ions, they collided with the rod, took 2 electrons from the rod. So if electrons are taken from the rod will be getting the positive charge. The rod will be getting the positive charge, right? When the zinc dye positives collided with the rod, took 2 electrons from the rod, got converted into zinc solid, and that zinc solid gets deposited on the rod. So tell me what happens to the number of zinc dye positives in the solution. Earlier, there were equal number of cations and anions. Now, one of the cation took 2 electrons from the rod, got converted into zinc solid, and that zinc solid got deposited on the rod. So in this solution, the cations are decreasing with time. So the solution is effectively going to get which charge? The solution is effectively going to get the negative charge. Do you see? On the rod, there is positive charge. On the solution, there is negative charge. So again, I must say, a potential difference got created. A potential difference got created between the rod and the solution. And this potential difference, which gets created between the rod and the solution, the potential difference that gets created between the rod and the solution is what you call as the electrode potential, which is represented by capital E. Which is represented by capital E. So electrode potential, which is represented by what? Which is represented by capital E. Now, my dear students, this electrode potential is basically of 2 types. One is called as oxidation potential. One is called as the reduction potential. See, here the electrode behaved like anode. Here the electrode, same electrode, it behaved like what? It behaved like cathode. When the electrode behaved like anode, rod got negative, solution got positive. When the same electrode behaved like the cathode, rod got positive, solution got negative. So first of all, in general, the potential difference between the rod and the solution, in general, the potential difference between the rod and the solution, you call that as the electrode potential. But this electrode potential, wherein rod gets negative, solution gets positive, this electrode potential is called as the oxidation potential. And this electrode potential is called as the reduction potential. So when the rod gets negative, solution gets positive. This electrode potential is called as oxidation potential. And similarly, when the rod gets positive, solution gets negative, this electrode potential is called as the reduction potential. So that's why I said electrode potential, I'm dividing into 2 categories: oxidation potential and reduction potential. Okay. Now people, this oxidation potential, there is one more way of representing it. You can write it like this. You can write it like this: EOX, oxidation potential. A reduction potential, you can write like this: ERED. Or oxidation potential, you can represent like this: E of M gives Mn positive. A reduction potential, you can represent like this: E of Mn positive gives M. Now, check carefully. Oxidation state of metal here is 0. 0 to plus N. 0 to plus N. Increase. Increase means oxidation. Oxidation means oxidation potential. Plus N to 0. Decrease in the oxidation state. Decrease in the oxidation state is something we call as reduction. So this term represents your reduction potential. So your oxidation, your electrode potential, I classified into 2 parts. One is oxidation potential, one is reduction potential, right? Now, my dear students, when the same oxidation potential or reduction potential, or in general, if I say, when this electrode potential or this electrode potential is measured under standard conditions, Now, you must be thinking, what are standard conditions? Standard conditions are nothing. When pressure is kept 1 bar, temperature is kept constant, generally 25 degrees centigrade, and concentration of the solution is kept 1 molar. These conditions are what you call as the standard conditions. So basically, if I do one thing, if I keep the pressure here as 1 bar, if I take the concentration of the solution 1 molar, if I keep the temperature constant, generally 25, that means I've got the electrode under standard conditions. And remember, when electrode potential is measured under standard conditions, what do you call that as? You call that as the standard electrode potential, which is represented by E naught. So what is E naught? E naught is basically the standard electrode potential, the potential difference between the rod and the solution, which is measured under standard conditions, which is measured when pressure is kept 1 bar, temperature constant, and when concentration is kept 1 molar, right? So you call the electrode potential as the standard electrode potential. So this also I can classify into 2 types. One is going to be your standard oxidation potential. One is going to be your standard reduction potential. Or you can represent it like this. E naught of M gives M N positive. This represents your SOP. Standard oxidation potential. Similarly, the standard reduction potential, you can represent it like this. E naught of Mn positive gives M, right? Or you can call it directly as the standard reduction potential. So standard electrode potential I classified into 2 parts. One is standard oxidation potential. One is your standard reduction potential. Okay. Now, my dear students, remember, for an element, remember, SOP is always equal to minus times its SRP. SOP is equal to minus times its SRP. For example, what does that mean? That means if I write E naught of zinc gives zinc dye positive. If I say this value is equal to 0.76 volt. First of all, look here. 0 to plus 2. Increase means oxidation. So this is your SOP. This is the SOP. Now, you can write the similar thing like this as well. E naught of zinc dye positive gives zinc. So plus 2 to 0. Decrease. Reduction. So this is SRP. So the SRP of the same is going to be minus 0.76 volt. Okay. So remember this particular point as well. Okay. SOP is always equal to minus times SRP. Now comes one more point. My dear students, SOP or SRP of an element, or let me write directly, of an electrode. SOP or SRP of an electrode is measured with the help of a reference electrode. And that reference electrode used here is called as the standard hydrogen electrode. The point is, how do we calculate the SOP values and SRP values of different elements? We calculate the SOPs and SRPs of different elements with the help of a reference electrode, which is what you call as the standard hydrogen electrode. Okay? Which is what you call as the standard hydrogen electrode. Now, what the standard hydrogen electrode is, how it is made, and what all things we have to remember about the standard hydrogen electrode. Try to understand carefully, guys, what I'll be saying. Mark the heading as standard hydrogen electrode first. Standard hydrogen electrode. Standard hydrogen electrode, SHE. It is a reference electrode which is used to calculate the SOP and SRP values of different elements. Okay. How this standard hydrogen electrode first of all is made. Have a look. Here, for example, I'm doing one thing. I'm taking a container. Let's say this is the container. In this container, my dear students, for example, I'm keeping H positive ions. I'm keeping H positive ions in the container. Okay. Let the concentration of H positives here in the container is 1 molar. 1 mole per liter. 1 molar. Okay. Now, for example, I'm taking a U-type tube like this. An inverted U-type tube like this. And in this inverted U-type tube, I'm taking a platinum wire. This is a platinum wire which I'm taking here. This is a platinum wire. Let me tell you, this is your platinum wire, which is, for example, coated with platinum black. I've taken a platinum wire here. Now, my dear students, from this opening, I'm introducing H2 gas. I'm introducing H2 gas at a pressure of 1 bar or 1 atm. I'm introducing H2 gas at a pressure of 1 bar or almost 1 atm. Now, people, when H2 gas is introduced here, when H2 gas is introduced, this H2 gas which is being introduced, it gets adsorbed on the surface of this platinum wire. It gets adsorbed on the surface of this platinum wire. It gets sticked on the surface of the platinum wire. Now, when the entire surface of the platinum wire gets covered with hydrogen molecules, now from outside, does it look a platinum wire to me or hydrogen wire? From outside, if I see it now, it looks like a hydrogen wire to me. So can I say this hydrogen wire is introduced in a solution containing its own ions? This hydrogen wire is introduced in a solution containing its own ions. So this electrode which we have made here, this is what we call as hydrogen electrode. This is what we call as hydrogen electrode. Since concentration is 1 molar, pressure is 1 bar or 1 atm. For example, I'm keeping the temperature 25 degrees centigrade. That means the conditions which I've used here, they are standard conditions. So I'll be calling this electrode as the standard hydrogen electrode. I'll be calling this as the standard hydrogen electrode. I hope you got to know how the standard hydrogen electrode is made. Now, my dear students, this hydrogen electrode, again, it can behave like anode. Again, it can behave like cathode. Now, think over it. When this hydrogen electrode behaves like anode, what is going to happen? Oxidation is going to happen. The H2 gas molecules which are there in the rod, they are going to undergo oxidation. H2 gas which is there on the rod undergoes oxidation, gets converted into H positives, and with that you will be getting 2 electrons. This is the reaction which you will have to remember. When hydrogen electrode behaves like the anode, this is the reaction that's going to happen. If the same hydrogen electrode behaves like the cathode, then what's going to happen? H positives in the solution, they will be colliding with the rod. They'll be taking the electrons from the rod. So just reverse the same reaction. It will be 2 times H positive plus 2 electrons gets what? Gets H2 gas. So the hydrogen electrode, it can behave like anode, it can behave like cathode. Okay. Remember, irrespective of the fact hydrogen electrode behaves like anode or behaves like cathode, let me tell you, the SOP as well as SRP, of hydrogen electrode is taken to be 0 volts. Is taken to be 0. Okay, it is taken to be 0. It is taken to be 0. The standard oxidation potential and the standard reduction potential of the hydrogen electrode, it is taken to be 0. It is taken to be 0. Or you can write the same thing like this as well. You can write E naught of H2 gives H positive. 0 to plus 1. Increase oxidation. So this is your SOP. Similarly, E naught of H positive gives H2. This is your SRP. Both the values are taken to be what? Both the values are taken to be 0 when it comes to the hydrogen electrode. SOP, SRP of hydrogen electrode is taken to be 0. Yeah? Perfect. I believe things are clear till here. Well, you must be thinking, are there some other reference electrodes? This hydrogen electrode is a reference electrode. You must be thinking, are there some other hydrogen electrode? Are there some other reference electrode? Absolutely, there are some other reference electrodes as well. What are the other reference electrodes that we have? What are the other reference electrodes that we have? One is called as calomel electrode. This is one of the reference electrodes, like your standard hydrogen electrode, right? Another is silver chloride electrode. These are another two reference electrodes which are used. Basically, this standard hydrogen electrode, it is comparatively difficult to make. The standard hydrogen electrode is comparatively difficult to make, right? So the other reference electrodes which are comparatively easy to make, that is your calomel electrode. Okay? Your silver chloride electrode. These are the other reference electrodes which we have. Now, my dear students, since I'm discussing electrode potential with you, now you must be thinking, what kind of knowledge, what kind of information this electrode potential gives us. So here comes the point, that is significance of electrode potential. That is significance of electrode potential. What is its significance? Where do we use this? Where do we use this? Try to understand properly what I'll be saying. Pretty much simple, guys. Have a look. Let me tell you this electrode potential. Electrode potential is of two types, oxidation potential and reduction potential. Remember, oxidation potential gives the tendency of an element to undergo oxidation. Oxidation potential gives the tendency of an element to undergo what? To undergo oxidation. Whatever tendency element has to undergo oxidation, that is checked by its oxidation potential value. Similarly, point number 2, a reduction potential gives the tendency of an element to undergo reduction. Reduction potential, it gives me the tendency of an element to undergo reduction. Oxidation potential gives me the tendency of an element to undergo oxidation. A reduction potential gives me the tendency of an element to undergo reduction. Now remember 2 points which I'm going to tell you now. Very, very, very important points. Remember, more the SRP of an element, more will be the tendency of an element to undergo reduction. More the SRP of an element, more will be the tendency of an element to undergo reduction. That element which undergoes reduction, what do we call that as? Oxidizing agent. So better will be the oxidizing agent. And remember, oxidizing agent, its oxidizing power. Better the oxidizing agent, more will be its oxidizing power. So this is the first statement which you guys need to remember. More the SRP of an element, more will be the tendency of an element to undergo reduction. Better oxidizing agent, more oxidizing power. Remember the statement like this only. Okay. Second point, my dear students. More the SOP of an element, more is the tendency of an element to undergo oxidation. More the SOP of an element, more is its tendency to undergo oxidation. Better will be the reducing agent. Better will be the reducing agent. And more will be the reducing power. These two statements are very, very, very important. So you need to remember them on priority, my dear students. So oxidizing power and SRP, they are directly proportional. Oxidizing power and SRP. Okay? Perfect, guys? So more the SRP, more the tendency of an element to undergo reduction, better the Oxidizing agent, more the oxidizing power. Clear with this, everyone? Clear to everyone? Quickly in the chats, people, quickly, everybody. Quickly, everyone. So can I conclude two statements here? What are the statements? Since SRP and oxidizing power, they are directly proportional. So I'll say oxidizing power is directly proportional to SRP. If it is directly proportional to SRP, it will be inversely proportional to SOP. Correct? Similarly, your reducing power. Reducing power is directly proportional to what? Your reducing power is directly proportional to SOP and inversely proportional to SRP. Remember these two statements. And see now how I'm going to utilize these concepts and how I'll be framing the questions. Simple, guys. Try to understand very properly what I'm going to say. For example, I'm taking 4 elements, A, B, C, and D. These are the 4 elements which we have, A, B, C, D. Okay. Let's say here I'm writing E naught of M gives Mn positive. E naught of M gives Mn positive. What does it represent? SOP or SRP? First tell me that. M gives Mn positive, 0 to plus N, increase, oxidation. So this represents SOP. Let's say this value is 1 volt, this value is 2 volt, this value is 3 volt, this value is 4 volt. So tell me, which one has got more SOP? This. More the SOP, more the tendency to undergo oxidation, better the reducing agent, more the reducing power. So this D will be having maximum reducing power here. Got it? For example, I'm writing like this. E naught of M gives Mn positive. What is it again? Again, it's SOP only. But now I'm keeping the values, for example, minus 1 volt, minus 2 volt, minus 3 volt, minus 4 volt. Now tell me which one has got more SOP now. This has got more SOP now. More the SOP, more the tendency to undergo oxidation, better the reducing agent, more the reducing power. So its reducing power here would be more. Okay. Similarly, for example, I'm writing E naught of Mn positive gives M. Is it SOP or SRP? Mn positive gives N. Plus N to 0, decrease, reduction. So this is SRP. Let's say this value is 1 volt, this value is 2 volt, this value is 3 volt, this value is 4 volt. Now which one has got more SRP? As you can see, this one has got more SRP. More the SRP, more the tendency to undergo reduction. More the SRP, more the tendency to undergo reduction. Better the oxidizing agent, more the oxidizing power. So its oxidizing power here will be more. For example, I'm writing something like this. Again, I'm writing E naught of Mn positive gives M. Okay. Let's say I'm taking the values as minus 1 volt, minus 2 volt, minus 3 volt, minus 4 volt. Tell me, which one has got more SRP now? I would say this one has got more SRP. More the SRP, more the tendency to undergo reduction. Better the oxidizing agent, more the oxidizing power. So its oxidizing power will be more. Am I clear with all this? Everybody in the chats? Am I clear with all this? Everybody in the chats? Quickly. Quickly, people, everybody. Did you understand the concept in a better way? Everyone in the chats, people? Perfectly done. Perfect. Let's try to see few questions on this electrode potential so that you'll get used to all the things. Look at the first question. You are given with 4 reactions. You have to check which of the following is the strongest reducing agent. Strongest reducing agent. Okay. Guys, have a look. Understand. Reducing agent. Reducing agent is the one. Which of the following is the strongest reducing agent? Reducing agent is the one which undergoes oxidation. Step by step, I'm telling you. Reducing agent is the one which undergoes oxidation. So that means the one that undergoes oxidation easily will be the better reducing agent. Now, which one undergoes oxidation easily? The one which has got more SOP. So you have to answer the question in terms of what? You have to answer the question in terms of SOP. What are these values? Are these SOP values or SRP values? If you look all the reactions, in every reaction, a reduction is happening. Gain of electron is happening. So Mg di positive is gaining electron. So Mg di positive is undergoing reduction. So this is the SRP of this Mg di positive. Zinc di positive gaining electrons. So this zinc di positive is undergoing reduction, right? SRP of zinc di positive. Nickel di positive is undergoing reduction. So this SRP. This is SRP. So these are basically the SRP values. These are basically the SRP values. Of what? Of all these ions which we have. But we have to answer the question in terms of SOP. So what I'll be doing? I'll be reversing all these reactions. When I reverse the reactions, the first reaction becomes Mg solid. Gives Mg di positive plus 2 electrons. Okay. Now its E naught value. Will it be minus 2.37 or plus 2.37? It will be plus 2.37 volt. Similarly, zinc solid gives zinc di positive plus 2 electrons. Its E naught value will be plus 0.76 volt. Similarly, nickel solid gives nickel di positive plus 2 electrons. Its E naught value will be plus 0.73 volt. I'm just reversing the signs, that's it. Fe solid gives Fe tri positive plus 3 electrons. Its E naught value will be plus 0.04 volts. Now tell me, are these SOP values now or SRP values? What do you think? Is it SOP now or SRP? See, magnesium is losing electrons. So magnesium now is undergoing oxidation. Magnesium is undergoing oxidation. Zinc is undergoing oxidation. Nickel is undergoing oxidation. Iron is undergoing oxidation. So these are basically the SOP values. These are basically the SOP values. SOP values of what? SOP values of all these metals here. Now, which one has got maximum SOP? This is the maximum SOP. So I would say magnesium has got maximum SOP. If magnesium has got maximum SOP, more the SOP, more the tendency to undergo oxidation, better the reducing agent. So which one is the better reducing agent? It's going to be magnesium. Yes, I believe it is clear to everyone. One more question of the similar pattern so that things will be like very much clear to you. We have to give the oxidizing power. We have to give the oxidizing power. Understand? Oxidizing power. Which has got more oxidizing power? The one that is the better oxidizing agent. The one that is the better oxidizing agent has got more oxidizing power. Now, oxidizing agent itself undergoes what? Reduction. So the one that undergoes reduction easily, better oxidizing agent. Now, which one undergoes reduction easily? The one that has got more SRP. The one that has got more SRP. So you are going to solve the question in terms of SRP. Now tell me, are we given with SOP values or SRP values? Everywhere gain of electrons is happening. Gain of electrons is what we call as reduction. So everywhere SRP is given. Now, cobalt tri-positive, gaining electron. So this cobalt tri-positive is undergoing reduction. Cerium plus 4 is undergoing reduction. Pb plus 4 undergoing reduction. Bi plus 3 undergoing reduction. Now, which one has got maximum reduction potential? Check the values. Which one has got maximum reduction potential? This is the maximum reduction potential value, right? Reduction potential means the reduction, which is undergoing reduction, cobalt tri-positive. So cobalt tri-positive, it has got maximum reduction potential, right? So if cobalt tri-positive has got maximum SRP, it will undergo reduction easily, better oxidizing agent, more oxidizing power. So cobalt tri-positive has got the highest. After cobalt tri-positive, which one is the next value? 1.67. That is the SRP of what? Pb plus 4. So Pb plus 4 is going to be the next. So it's option B. That is going to be the correct answer of the question. Did you understand, everybody? If yes, then tell me the answer of this question. The reducing power. You have to give me the order of reducing power. Now, more reducing power means better reducing agent. Better reducing agent means it should undergo oxidation easily. Which undergoes oxidation easily? Which has got more SOP. So the question has to be solved in terms of SOP. What are these values? These are SRP values. As you can see, everywhere reduction is taking place. So this is SRP of zinc dipositive, SRP of calcium dipositive, SRP of magnesium dipositive, SRP of this. But I have to solve the question in terms of SOP. So reverse the reactions. So first reaction becomes zinc solid, gives zinc dipositive plus 2 electrons. Now this is not the reduction reaction. Now this is the oxidation reaction. And which one is undergoing oxidation? Zinc is losing electrons. So zinc is undergoing oxidation. So its E naught value will be plus 0.76 volt. Similarly, this was the E naught of zinc. Similarly, what would be the E naught of calcium? SOP of calcium. SOP of calcium will be plus 2.87 volt. SOP of magnesium. SOP of magnesium will be plus 2.36 volts. Similarly, SOP of nickel would be plus 0.25 volts. Now tell me which has got maximum SOP. These are all SOP values. These were the SRP values of these ions which were undergoing reduction. Now these are the SOPs of these metals which are undergoing oxidation. So which one has got maximum SOP now? This one, calcium. So if calcium has got maximum SOP means maximum reducing power. Now after calcium, the next is going to be magnesium. Next is going to be magnesium. So it's going to be option B. Did you understand how this sort of equation is to be solved? Everyone, people, everyone. Did you understand? Yeah? Perfect, guys. Perfect. Now let's move on to one more topic. What is that? That is your EMF. EMF. How do we exactly define the term EMF? How do we exactly define the term EMF? Let me tell you in simple words, EMF is defined as the potential difference between the electrodes. When the cell is not in use. That means when no current is drawn from the cell. When no current is drawn from the cell. See guys, first of all, you know your Daniell cell. What does the Daniell cell do? Daniell cell produces current. Daniell cell produces what? Daniell cell produces current. Now, current flows only due to potential difference. In case of your Daniell cell, you have got zinc electrode and you have got copper electrode. You know that? This is your zinc electrode, this is copper electrode. And connected externally as well as internally. This is your Daniell cell. What does it do? It produces current. Current flows due to what? Potential difference. So that means, my dear students, there will be potential difference between these two electrodes. There will be potential difference between these two electrodes, due to which current will be produced. There will be potential difference between these two electrodes, due to which current will be produced. Now the maximum potential difference between the electrodes, when the cell is not in use, when no current is drawn from the cell, you call that maximum potential difference as the EMF. You call that maximum potential difference as the EMF. Okay? I'm not going into much details of EMF. Perfect? I'll just teach you all the things which can be asked in your exam. Nothing more, nothing less. Okay? Otherwise, let me tell you, this EMF is measured by an instrument called as potentiometer. This EMF is measured by an instrument called as potentiometer. But let's not talk about that. Let's not exactly see how potentiometer is used to calculate the EMF and all, right? That's of no use to us for our examination purpose. Okay? Just remember one thing. EMF is nothing but it is the maximum potential difference between the electrodes when the cell is not in use. Yeah? You can remember it like this as well. You can remember it like this as well. For example, I got a battery. I got a cell from the market. Let's say I got a cell from the market. This is your battery, which I got from the market. The battery is right now in the wrapper only. It is wrapped. Okay, it is wrapped. So the battery is right now not in use. It is not in use. On the wrapper, they have mentioned 5 volt. On the wrapper, they have mentioned the voltage of the battery is 5 volt. So right now, the cell is not in use. It is not in use. Now, when I put the same battery in this remote, for example, the battery starts working. The battery starts working. So with time, when the battery starts working, with time, the potential difference between the electrodes here in this battery will be 4 volts, then 3 volts, then 2 volts, then there'll be a time when it will be 0 volt. The when it is 0 volt, that means the battery will be dead. You can remember it like this, okay? That means at 0 volt, the battery is dead. At this particular voltage, the battery was working. At this particular voltage, the battery was working. At this particular voltage, the battery was working. Here, the battery was not in use. The cell was not in use. Now, which one is the maximum potential difference among all these? 5 volts. This is the maximum potential difference when the cell is not in use. And the maximum potential difference between the electrodes when the cell is not in use, you call that as the EMF. So, this 5 volt is what I call as the EMF of the cell. Rest all the other voltages apart from 5 volts, this 4 volt, 3 volt, 2 volt, they are called as cell voltage. Maximum potential difference is called as EMF. All the other voltages are called as normal cell voltage. Okay, you can remember it like this. You can remember it like this. In reality, if we have to understand EMF, then we have to study potentiometer first. Okay, then after studying potentiometer, then I can tell you what EMF exactly is. For that, you have to take a galvanic cell. You have to connect that with the external battery in reverse polarity, right? Then only we can talk about those things. But that's of no use to us right now. So just remember, the potential difference between the electrodes when the cell is not in use, right, when no current is drawn from the cell, is called as EMF. Now, my dear students, one more thing. When EMF is measured, under standard conditions, the maximum potential difference between the electrodes when the cell is not in use, that's called as EMF. When EMF is measured under standard conditions, you call that as the standard EMF, which is represented by E0 cell. You call that as the standard EMF, which is represented by E0 cell. First of all, EMF is represented by what? EMF is represented by E cell. Your standard EMF is represented by E0 cell. So if you have your galvanic cell in your mind, if you have your Daniel cell in your mind, the maximum potential difference between the electrodes when the cell is not in use, that's called as EMF. When that maximum potential difference is measured under standard conditions, you call that as a standard EMF, which is represented by E0 cell. And remember, my dear students, this E0 cell is nothing but it is equal to E0 of cathode minus E0 of anode. This E0 cell is nothing but it is E0 of cathode minus E0 of anode. What is this E0 of anode, E0 of cathode here? E0 of cathode represents the SRP of cathode. E0 of anode again represents SRP of anode. So SRP of cathode minus SRP of anode. That gives me the E0 cell. That gives me the standard EMF of the cell. Well, my dear students, you can do one more thing as well. You can convert this result in one more form. See, I use the term SRP of cathode here. SRP of cathode. Instead of SRP of cathode, you can write minus times SOP of cathode. You can write minus times SOP of cathode. In the middle, the sign is minus. This is SRP of anode. you can write minus times SOP of anode. So minus minus plus. The result becomes SOP of anode minus SOP of cathode. You can remember the result like this as well. You can remember the result like this as well. But no need to remember two results, right? Just remember this particular result. You can make one more result. See, this result, in this particular result, both are SRPs. In this particular one, both are SRPs. You can keep one as SOP, one as SRP, right? You can keep one as SOP, one as SRP. So you can form other results as well. But our priority is this particular result, that is E naught cell, is equal to E naught cathode minus E naught anode. E naught cathode is SRP of cathode. E naught anode is SRP of anode. Simple. This particular result is important. Now guys, try to understand where I use this particular result. I have a proper eye on the screen now. Because something which I'm going to tell you now, that is something very, very, very important. Okay? So try to understand what all things I'm going to tell you now. For example, I'm writing something like this. E naught of A positive gives A is equal to 1 volt. Here I'm writing E naught of B positive gives B is equal to 3 volt. If I ask you how many electrodes do I have right now? Can I say I have 2 electrodes? I have 2 electrodes. For example, I am connecting these electrodes externally as well as internally with the help of salt bridge. I'm connecting these electrodes externally as well as internally with the help of salt bridge. Can I say after connecting these electrodes, I will be getting a complete galvanic cell? A complete galvanic cell consists of 2 electrodes. I took 2 electrodes. I connected them externally as well as internally. So I will be getting a galvanic cell. Now the point is, how do you calculate the standard EMF of that galvanic cell? And you know, standard EMF of the galvanic cell is nothing but, that is E naught cathode minus E naught anode. SRP of cathode minus SRP of anode. Now you guys are going to tell me one thing. See, is this SOP or SRP? Plus 1 to 0, decrease, reduction. So this SRP. Plus 1 to 0, decrease, reduction. So this SRP. Which one has got more SRP? This one. More the SRP, more the tendency to undergo reduction. And reduction takes place at cathode. So this will be your cathode and this will be your anode. Since you identified your cathode and anode. So what was this E naught C? This was SRP of cathode. And this was SRP of anode. This was your SRP of anode. SRP of cathode is how much? SRP of cathode is 3 volt minus SRP of anode. SRP of anode is 1 volt. The value comes out to be 2 volts. So this 2 volts is going to be the standard EMF of the cell. Simple. Did you understand? Let me take one more example so that things will be more clear to you. For example, here I'm writing E naught of M gives Mn positive. Let's say this is minus 5 volt. Here I'm writing E naught of N negative gives N. It is equal to 5 volt. Okay. So how many electrodes do I have right now? I have again got 2 electrodes. Connect them externally as well as internally. I will be getting a complete galvanic cell. Now we have to calculate the standard EMF of that complete galvanic cell. We have to calculate E naught cell. First of all, tell me one thing. What is this particular value? Is this SOP or SRP? See, 0 to plus N, increase, oxidation. So this is SOP. Minus 1 to 0, increase. Minus 1 to 0, increase, oxidation. So this is SOP. Do I have any result? Do I use the result in terms of SOP or SRP? I use the result in terms of SRP. So convert this SOP into SRP. So its SRP will be plus 5 volt. Its SRP will be minus 5 volt, right? So I got the SRP values. Now tell me, which one has got more SRP, first or second? First has got more SRP. More the SRP, more the tendency to undergo reduction, and reduction takes place at cathode. So this is going to be your cathode, this is going to be your anode. Since you identified your cathode and anode, now what would be E naught cell? E naught cell would be E naught cathode, SRP of cathode, minus SRP of anode. SRP of anode is minus 5. So 5 minus minus 5 comes out to be 10 volt. So 10 volt is the standard EMF of the cell. Understood? Understood, people? One more example. With that, things will be more clear. Let's say I'm writing E naught of A gives A die positive. This is equal to minus 3 volt. Okay. E naught of B die positive gives B is equal to 4 volt. I've got again 2 electrodes. Again, I've got 2 electrodes. Again, I'm connecting them externally as well as internally. So I'm getting a complete galvanic cell. Now, 0 to plus 2, increase, oxidation. So this is your SOP. Plus 2 to 0, decrease. Decrease means reduction. So this is your SRP. Now, this is already your SRP, but here it's SOP. So convert this SOP into SRP. So it will be plus 3 volt. This is SRP. Now compare the SRP values. Which one has got more SRP? This has got more SRP. More the SRP, more the tendency to undergo reduction. Reduction takes place at cathode. So this is your cathode, this is your anode. Since you identified your cathode and anode, now you can easily check E naught cell. And E naught cell is going to be nothing but E naught cathode minus E naught anode. E naught cathode means SRP of cathode. SRP of cathode is 4 volt minus E naught anode, SRP of anode. SRP of anode is how much? SRP of anode is 3 volt. So 4 minus 3 comes out to be nothing but 1 volt. So this is how, if you will be having 2 electrodes, if you connect them externally as well as internally. If you connect them externally as well as internally, you'll be getting a complete galvanic cell. And from a complete galvanic cell, you can easily calculate what? You can easily calculate the standard EMF of the cell. If I'm clear, tell me once in the chats. Right, people? All clear till here? Okay. So one question for you. Tell me the answer of this one. Sir, N to N negative. Where was N to N negative? Just a second. Are you talking about this one? This N negative to N, minus 1 to 0. Increase. Increase means oxidation. So this is SOP. So its SRP will be minus 10. Is this? This correct only. N to N negative will be 0 to minus 1. 0 to minus 1 means SRP. Decrease. Okay. All right. Tell me the answer of this question. As far as the question is concerned, the standard oxidation potential values are given. Standard oxidation potential values are given. But do I need standard oxidation potential values? No. I don't need SOP values. I need SRP values. So what would be the SRP of this one? SRP of the first one will be minus 0.76. SRP of the second one will be minus 0.41. I got their SRPs. I got their SRPs. Now, which one is more? This is more. More the SRP, more the tendency to undergo reduction. Reduction takes place at cathode. So this is cathode, this is anode. Basically, your iron is going to behave like cathode and your zinc is going to behave like anode. Now, what am I supposed to calculate? I'm supposed to calculate E naught cell. E naught cell is nothing but E naught cathode minus E naught anode. So this is SRP of cathode. SRP of cathode is minus 0.41 minus SRP of anode. That is minus 0.76. The value comes out to be plus 0.35 volt. Okay. So this is the E naught cell. All clear with this? Everybody in the chats? All clear with this? Perfect. Okay, now comes something important. What is this important thing? See guys, if I ask you one thing, you tell me in the chats, okay? If I ask you, in order to make a galvanic cell, how many electrodes are required? Just tell me the answer of this one. In order to make a galvanic cell, how many electrodes are required? Your answer will be 2 electrodes are required. Your answer will be 2 electrodes are required. If I give you any 2 electrodes, if I give you any two electrodes, okay, and if you connect them externally and internally, you will be getting a galvanic cell, complete galvanic cell. Now the point is, will that galvanic cell will work or not? Will that galvanic cell works or not? That is the question. I am telling you, in order to make a galvanic cell, you need two electrodes. Connect them externally, internally. No doubt you made a galvanic cell, but the point is, will that work or not? Will that produce current or not? Okay, that will be told by this particular topic. That will be given by this particular topic. This particular topic is going to tell us whether the galvanic cell will work or not. So first of all, I am going to give you one result, which I'm not going to derive because the derivation is of no use to us right now. Okay, I'm just going to give you the result and we'll see how it's applied. The result is delta G is equal to minus NFE cell. This is the relation between delta G and EMF of the cell. If you write the same equation under standard conditions, then instead of delta G, you will write delta G naught is equal to minus NFE naught cell. Minus NFE naught cell. The same equation which you have written under which conditions? Under standard conditions. Now guys, have the proper eye on the screen and understand what exactly I'm going to tell you. If you take two electrodes, if you connect them externally and internally, you will be getting a complete galvanic cell. Now, will that galvanic cell work or not? That decides on just one thing. Whether the cell reactions in the cell, whether they are happening on its own or not. That means, in other words, I can say, whether the cell will work or not, it depends on just one thing. Whether the cell reactions are spontaneous or not. Whether the reactions are happening at anode and cathode, whether the reactions are happening on its own or not. If the reactions are happening on its own, if the cell reactions are spontaneous, the cell will work. If the cell reactions are non-spontaneous, if they are not happening at anode cathode, so the cell will not work. As simple as that. Okay, so I would say something like this. For a cell whose delta G for the reactions will be negative. Delta G for the reaction negative means? Delta G negative means reactions are spontaneous. For any spontaneous process, delta G for the system is negative. So for example, I've got a galvanic cell whose delta G is negative. Delta G negative means minus NFE cell. This term is negative. When can this particular term be negative? This entire term can be negative only if E cell is positive. If E cell is positive. So if you have got a galvanic cell whose delta G is negative, or you can say whose E cell is positive, I would say in that galvanic cell, the cell reactions will be spontaneous. The cell reactions will be spontaneous. That means at anode automatically oxidation will take place. At cathode automatically reduction will take place. Or in short, I would say electrons will move from anode to cathode. Current will go from cathode to anode. So the cell works like a normal galvanic cell. The cell works like a normal galvanic cell, wherein electrons, they move from anode to cathode and current goes from cathode to anode. Okay? Is this particular point clear? The second point, which is similar to this. What is that? If you have got a complete galvanic cell whose delta G is positive, delta G positive means minus NFE cell is positive. Minus NFE cell can be only positive if E cell is negative. If E cell is negative. So if you have got a galvanic cell whose delta G is positive or E cell is negative, in that galvanic cell, cell reactions, if delta G is positive, that means cell reactions are non-spontaneous. That means the reactions won't take place on its own. If the cell reactions are non-spontaneous, that means the cell does not work. The cell does not work like a normal galvanic cell. Understood? Similarly, the third point. If delta G for the cell is 0, what does that mean? That means minus NFE cell value is 0. It is possible only if E cell value is equal to 0. E cell 0 means there is no potential difference between the electrodes. If there is no potential difference between the electrodes, the cell does not produce any current. And this state is called as the equilibrium state in the cell. The cell is present at its equilibrium state. This we have to discuss in detail in some time. Just remember it for now. Just remember it for now. Are all these things clear? If I quickly summarize this, let me tell you, for any galvanic cell to be working, the cell reactions in the galvanic cell must be spontaneous. And for the cell reactions to be spontaneous, delta G for the cell should be negative or EMF should be positive. That is the criteria for the cell to work. Am I clear? Am I clear, my dear students? Everybody? Okay? Is this clear? This particular point we have to discuss in detail after some time. Now, if this is clear, guys, then there is something more which I would want to share with you. What is that? Whenever in a question you are supposed to calculate delta G, let me tell you the SI unit of delta G, the SI unit of Gibbs free energy change is nothing but, it is Joule. It is Joule, delta G. Sometimes in the question they'll ask you to calculate the non-PV work. Sometimes in the question they'll ask you to calculate the non-PV work, or they might ask you to calculate the useful work. They might ask you to calculate the useful work. Whenever you are supposed to calculate useful work or non-PV work, that means you have to calculate the value of delta G. Sometimes they can play with the language of the question as well. Sometimes in the question, they might ask you to calculate useful work, to calculate non-PV work. That means indirectly they are asking you to calculate delta G. And delta G is nothing but minus NFE cell. The third point. Delta G is an extensive property. Delta G is an extensive property. And extensive properties can be added or subtracted directly. Delta G is an extensive property, and let me tell you, extensive properties can be added or subtracted directly. Whereas, if I talk about your E, electrode potential, or EMF, it is an intensive property. It is an intensive property. So, these values cannot be added or subtracted directly. Delta G can be added or subtracted directly because delta G is an extensive property. Okay? See, it is basically the point from Thermodynamics chapter. Thermodynamics says that extensive properties can be added or subtracted. Intensive properties cannot be added or subtracted directly. Okay? So let me tell you, delta G, it is the example of your extensive property. So it can be added or subtracted, whereas E cannot be added or subtracted directly. Okay? I believe I'm clear. Okay, one more thing. You need to remember it as well. For example, you have got a reaction like this. A plus B gives A positive plus B negative. Let's say this is a reaction, general reaction. For example, its E naught value is equal to, let's say, some X volt. Okay. Its E naught value will be some X volt. Or, let me make things a little clear to you. Little easy to you. For example, I've got Mn positive plus N electrons gives M. Okay, let's say its E naught value is equal to, for example, 2 volt. Okay, remember, when you multiply this reaction by some number, nothing happens to its E naught value. Remember this point directly. When you multiply this reaction by some number, nothing happens to its E naught value. When you divide this reaction by some number, nothing happens to its E naught value. But when you reverse the reaction, you have to change the sign. Sign becomes -2 then. Remember these 3 points as well. Okay? So let me summarize this point, whatever I've told you. The point is, when a reaction is multiplied by some number, nothing happens to its E naught value. Okay? You can modify it. You can write it as when a reaction is multiplied or divided by some number. Okay? Multiplied or divided by some number. Nothing happens to its E naught value. Perfect. But when a reaction is reversed, the sign of E naught is also reversed. When a reaction is reversed, sign of E naught is also reversed. Perfect. Now these points are very, very, very important when it comes to the questions. Okay, and what kind of questions can be asked from this topic? First one is the simplest among all. The question is, calculate delta G for the reaction when the concentration is equal to 1 molar, temperature is 298 Kelvin. So that means we have to calculate delta G under standard conditions. Delta G under standard conditions is delta G naught basically. So delta G naught is minus NF E naught cell. Minus NF E naught cell. Minus NF E naught cell. So first of all, the cell that is given to me, I need to calculate its E naught cell. What is E naught cell? E naught cell is nothing but that is E naught cathode minus E naught anode. E naught cathode means SRP of cathode. Few minutes back I've told you. E naught anode means SRP of anode. SRP of anode. Now, in this reaction, copper is undergoing oxidation. Oxidation takes place in anode. So this copper electrode is your anode. That means this tin is your cathode. So you identified your anode and cathode. Just a second, guys. I think the values are wrong in the question. Because in the question, they have shown copper undergoing oxidation. Right? If copper is undergoing oxidation, so copper has to be anode. That means this tin has to be cathode. If this tin has to be cathode, that means its SRP should be more. But here they have shown SRP of this is less, SRP of this is more. No. So that means the question will be like this. It won't be minus, it will be plus, and this will be minus. This would be the question. This would be the question. Okay? This would be the question. Did you understand? I'll give the break at 9, guys, not now. Did you understand? Now, I identified my cathode and anode. Now, what is E naught of cathode, SRP of cathode? SRP of cathode is given as 0.16 minus SRP of anode is given to me as minus 0.34. The value comes out to be 0.50 volt. If E naught cell is 0.50 volt, now tell me, delta G naught is equal to minus. What is the N value for the reaction? If you look at the reaction carefully, I have taught you how to calculate N value. N value for the reaction is 2. This F represents Faraday's constant. And the value of Faraday's constant, you should be knowing, 96500 coulomb. So F is a constant, Faraday's constant, whose value is 96500 coulomb. E naught value is equal to 0.5. It is just a matter of calculation. 0.5 into 2 is 1. So delta G naught will come out to be minus 96500, and answer is going to be in joules, right? Since you have taken all the parameters as per SI system, so delta G naught will also come as per SI system, and the unit of delta G as per SI system is joule. Okay. Now comes one more question, guys. This is one of the type of the question which can be asked from just the formula. The second one. You are given with 3 reactions. Out of 3 reactions, E value of 2 reactions is given to us. Okay. We have to calculate E value for the third reaction. Let me tell you, my dear students, the reaction for which E is to be calculated, we are supposed to make that reaction out of those reactions whose E value is given. The reaction whose E value is to be calculated, we are supposed to make that reaction out of those reactions whose E value is given. Now understand, if I call this as equation number 1, if I call this as equation number 2, I'm calling this equation number 3. So I have to make third equation from first and second. Now think over it. How can you make third reaction from first and second? It's pretty much simple. If you add these two reactions, Cu positive cancels out. It becomes Cu di positive, 1 and 1, 2 electrons gives Cu solid. Cu di positive plus 2 electrons gives Cu solid. So basically, third reaction we are getting when we are adding first and second. Now, if you are thinking that instead of third you will write E3, instead of 1 you are writing E1, instead of 2 you can write E2. If you are thinking like this, that means you're gone, you're doomed. Why? As I told you a few minutes back, E is not an extensive property, it's an intensive property. And intensive properties cannot be added or subtracted directly. Intensive properties cannot be added or subtracted directly. Extensive properties can be added or subtracted directly. So that means, my dear students, you are not going to solve this question in terms of E. You will be solving this particular question in terms of delta G, because delta G is extensive and you can add or subtract extensive properties directly. So how we are going to solve this? Instead of third, you write delta G3. Instead of 1, you'll write delta G1. Instead of 2, you'll write delta G2. Now delta G3 is nothing but minus N3FE3 is equal delta G1 minus N1FE1, delta G2 minus N2FE2. So first of all, F everywhere cancelled, multiply through with minus sign. So E3 value will be equal to N1E1 plus N2E2 divided by N3. Now as per the question, E1 is given, E2 is given, E1 is given, E2 is given. Well, now what is this N1, N2, N3? This is the value of your N1. So N1 value is 1 electron. Here also 1 electron. So N2 value is also 1. Here you can see 2 electrons. So N3 value is 2. So N1 we know, N2 we know, N3 we know, E1 we know, E2 we know. So put the values, get the E3 value. Did you understand? Did you understand, people? Everybody? Did you understand? Let me give one more question of the similar format so that you will understand it. You have got a reaction Fe tri positive plus 3 electrons gives Fe solid. Fe2 positive plus 2 electrons gives Fe solid. This is gives here, okay? This is gives, arrow. And this is also arrow. So I'm basically given with 3 reactions, correct? I'm given with 3 reactions, out of which E value for 2 reactions is given and E value for third reaction is to be calculated. That's the question. E value for 2 reactions is given. E value for third reaction is to be calculated. What am I supposed to do? I'm supposed to make this equation out of these 2. Calling this is equation number 1. Calling this is equation number 2. Now third equation I have to make from first and second. Now how can we make third equation? See, in the third equation you have 1 electron here. So what you have to do? You have to subtract these 2. You have to subtract second from first. So if this is positive, this becomes negative. If this is plus 2 electrons, this becomes minus 2 electrons. This becomes minus Fe. So when you subtract these 2, what do you get? You get Fe tri positive plus 3 electrons minus Fe di positive minus 2 electrons. This and this cancels, nothing on this side. So 3 electrons minus 2 electrons is 1 electron. So it becomes Fe tri positive plus 1 electron. Take this minus Fe di positive on that side, it becomes plus Fe di positive. Was I supposed to make this reaction only? Check it out. I was supposed to make this reaction only. Yeah? I was supposed to make this reaction only. How did I make this reaction? How did I make the third equation? Third equation I made when I subtracted second from first. When I subtracted second from first. Now, Am I going to do the same operation with their E values? No. I'm going to do the same operation with their delta G values. So this is going to be delta G3 is equal to delta G1 minus delta G2. Delta G3 is nothing but minus N3FE3 is equal. Delta G1 is minus N1FE1 minus becomes plus N2FE2. So F everywhere cancels. If you multiply with minus sign throughout, so what do you get at the end? You'll be getting E3 is equal to N1E1 minus N2E2 divided by N3 value. Now N1, N2, N3 are given. This is our N1 value. This is our N2 value. This is our N3 value. So N1, N2, N3 are given. Even E2 values are also given. Even E2 values are also given. Just put the values and get the value of E3, which you were supposed to calculate. As simple as that. Yes? I believe I'm clear to everyone. I believe I'm clear to everyone. Let me solve one more question for you. Look at this particular question. Let me write these reactions first of all. The first reaction is MnO4 negative gives what? It gives MnO4 dinegative. Okay, its E1 value is, for example, given to me as 1 volt. Second reaction is MnO4 dinegative gives MnO2. Its E2 value is equal to 2 volt. Third one, MnO2 gives Mn di positive. Its E3 value is, for example, equal to 3 volt. MnO4 negative gives Mn di positive. Its E4 value is to be calculated. Now the reaction whose E value is to be calculated, you are supposed to make that reaction. But before that, in the first reaction, what about the electrons? If you look carefully, the oxidation state of manganese here will be plus 7. The oxidation state of manganese here will be plus 6. Plus 7 to plus 6, decrease, reduction. How many? Change in the oxidation state, final minus initial. It will be 1 electron. So basically MnO4 negative would be gaining 1 electron, then getting converted into MnO4 dinegative. Similarly, oxidation state of manganese here will be plus 6. Here it will be plus 4. Plus 6 to plus 4, again decrease, reduction, gain of electrons. How many? 2. Because plus 6 to plus 4. Similarly, this is plus 4 here. Plus 4 to plus 2, decrease, reduction, again 2. This is plus 7 here. Plus 7 to plus 2. So this has to be 5 electrons. Yeah? Now guys, I am basically supposed to make this particular reaction. Now think over it. How will you make this particular reaction? How will you make this particular reaction? The reaction which we have to make, we need 5 electrons here. How do you get 5 electrons? 2 plus 2 plus 1. 2 plus 2 plus 1 is 5. So basically, I can do one thing. I can say fourth equation is made when you add first, second and third. And whatever operation you are doing with the reactions, same operation you have to do with the delta G values. So this will be delta G4 is equal to delta G1 plus delta G2 plus delta G3. Now, delta G4 will be equal to how much? It will be minus N4FE4 is equal to minus N1FE1 minus N2FE2 minus N3FE3. So F everywhere cancels out. Multiply with minus sign and at the end you will get E4. E4 will be N1E1 plus N2E2 plus N3E3 divided by what? Divided by N4. Now, N1 is 1, N2 is 2, N3 is 2, N4 is 5. So N1, N2, N3, N4. We have all the values. E1, E2, E3. E1, E2, E3 is given. Put the values and get the E4 value. That's all. Is this particular concept clear? Did you understand how this sort of a question is to be solved? I would want answers from everybody. Will you be able to solve this sort of a question if it is asked? Everyone in the chats, guys. Everyone in the chats. Quick. Quickly. Quickly. After this topic, I'll give you the break. Electrochemical series. Perfectly done. So in short, one thing you have to remember. The reaction whose E is to be calculated. You are supposed to make that reaction out of those reactions whose E value is given. Perfect, guys. Now let's have a look on this electrochemical series. What is an electrochemical series, first of all? My dear students, simple. When these elements, when the metals, these are metals first of all, when the metals are arranged on the basis of their increasing SRP values, when the metals are arranged on the basis of their increasing SRP values, okay, the series of elements which you get here is called as electrochemical series. You would have seen it already. You would have seen it already. When different metals are arranged on the basis of their increasing SRP values, the series of elements which you get here is called as your electrochemical series. So this is your lithium, potassium, calcium, sodium, magnesium, aluminum, manganese, right? This is your electrochemical series, wherein I have arranged the metals as per their increasing SRP values. Now guys, see what you have to do. This hydrogen is our reference. This hydrogen is our reference. And you know SRP of hydrogen is 0. SRP of hydrogen is 0, right? That means all the elements which are before hydrogen, all the elements which are before hydrogen, their SRP value will be negative. Simple. I've arranged these elements on the basis of their increasing SRP values. So if SRP of hydrogen is 0, that means the SRP of all these metals which are coming before hydrogen will be negative. Or in short, I would say, the metals which come before hydrogen, their SRP is less. The metals which come before hydrogen, their SRP is less. The elements which come after hydrogen, their SRP is more. Okay, this is the first point which you have to understand. Before hydrogen, you have got lesser SRP elements. After hydrogen, you have got more SRP elements. Yeah? Now, what kind of information this electrochemical series gives us? First of all, this electrochemical series gives me the idea about the oxidizing power of an element, which we have already discussed. The one that has more oxidizing power is the better oxidizing agent. The one which is the better oxidizing agent, that will undergo reduction easily. The one that undergoes reduction easily, that has got more SRP. Right? So, your oxidizing power, it is directly proportional to what? SRP, and inversely proportional to SOP. This is something which we have already discussed. Something that we have already discussed. Right? Reducing power. More the reducing power, better the reducing agent. Better the reducing agent, more is its tendency to undergo oxidation. That means more would be its SOP. Right? So reducing power is directly proportional to what? SOP. Inversely proportional to what? SRP. Yeah? Perfect. This is also something which we have already discussed. This is something which we have not discussed. Predicting displacement reactions. For example, if you look at this particular reaction, you have got a solution of copper. You have got a solution of copper. And in this solution of copper, you are introducing zinc. In this solution of copper, you are introducing what? Zinc. Now, what the zinc is doing? Zinc is displacing copper from its solution. Zinc is displacing copper from its solution. Right? Zinc is going to displace copper from its solution. So what do you get? You get here ZnSO4 plus copper. You took an aqueous solution of copper. And in this solution of copper, you are introducing zinc. What the zinc is doing? Zinc is displacing copper here and getting converted into zinc is displacing copper. So copper, when being displaced, it gets converted into zinc sulfate. When this displacement happens, that's the point. When this displacement happens, try to understand. What is the oxidation state of zinc? 0. Oxidation state of zinc here, +2. So zinc is undergoing oxidation. Zinc is undergoing oxidation. Zinc is undergoing oxidation. Okay. If this is undergoing oxidation, that means this is undergoing, this copper is undergoing, copper dipositive is undergoing reduction. Copper dipositive is undergoing reduction. The one that undergoes oxidation easily, its SOP will be more. Its SOP will be more. If its SOP is more, that means its SRP will be less. Its SRP will be less. Can I say that element whose SRP will be less, will undergo oxidation? That means I can say, in other words, that element whose SRP will be less, that will displace the element from its solution. That element whose SRP will be less, that will be displacing one more element from its solution like this. Did you understand? Now, which elements are there whose SRP is less? All those elements which come before hydrogen. All those metals which come before hydrogen in electrochemical series, they can displace other metals from their aqueous solution. They can displace other metals from their aqueous solution. So which metal can displace other metal from its aqueous solution? That metal whose SRP is less can displace the other metal from its aqueous solution. Did you understand this particular point, everyone? In the chats, guys, quick, then only and move ahead. Did you understand this particular point? So if I would want to summarize it, I can summarize it like this. The metal that comes before hydrogen, that means I'm talking about that metal whose SRP is less, can displace other metal that comes after hydrogen from its aqueous solution. Okay? Remember this particular point. Now I'm asking you one simple question. Let's say I'm writing a reaction. Copper solid plus zinc sulfate gives copper sulfate plus zinc. Will this reaction happen? Is this reaction going to happen? Can copper displace zinc? See, can copper displace zinc? Quickly. This is zinc here. Copper is here. Copper is after hydrogen. Zinc is before hydrogen. Zinc can displace copper from its solution. Copper cannot displace zinc from its solution. Right? So this reaction cannot happen. Copper cannot displace zinc from its solution. Did you understand? Guys, say it in the chats quick. Okay, one more important point. Those metals which come before hydrogen in electrochemical series can liberate hydrogen from the solution of an acid like HCl. See, you would have seen one reaction in your notebooks, textbooks, wherever. Mg solid plus HCl. Mg solid plus HCl. It gives what? It gives MgCl2. With that, hydrogen gas is produced. Have you seen this sort of a reaction? This sort of a reaction you would have seen many a times. Or aluminium plus HCl. Aluminium plus HCl gives AlCl3 plus hydrogen gas. So this metal is introduced in an acidic solution. This metal is introduced in an acidic solution. And what is being liberated? Hydrogen gas is being liberated. So if you see carefully what is happening to metal, its oxidation state is 0. And its oxidation state is +2. Increase in oxidation state means oxidation. So this metal here is undergoing oxidation. I would say when metal undergoes oxidation, then only hydrogen gas will be produced. When metal undergoes oxidation, then only hydrogen gas will be produced. Now, which metal undergoes oxidation easily? The one that has got more SOP. More SOP means lesser SRP. So that metal which has lesser SRP, can produce hydrogen gas, right, in an acidic solution. That metal whose SRP will be less, it can produce hydrogen gas when it is introduced in an acidic solution like HCl. Or in other words, which metals have got lesser SRP? Those metals which come before hydrogen. Those metals which come before hydrogen in the electrochemical series can easily liberate hydrogen gas from a solution of an acid like HCl. Got this particular point as well? But remember this one, guys. Remember this one. Remember this one. When a metal which will be having lesser SRP, which comes before hydrogen, when a metal which will be having lesser SRP, which will be coming before hydrogen, when that metal is introduced in an acidic solution of HNO3, when a metal which comes before hydrogen, which has got lesser SRP, when it is introduced in an acidic solution of HNO3, at that point of time, hydrogen gas is not liberated. Hydrogen gas is not produced. At that point of time, oxides of nitrogen are produced. At that point of time, oxides of nitrogen are produced. Remember this particular point. Okay? Because NO3 negative, that is a better oxidizing agent than that of H positive. So remember it directly, guys. See, what all statements you have to remember. Number one, that metal which comes before hydrogen, it can displace other metal from its aqueous solution which comes after hydrogen. Point number one. Point number two, that metal can liberate hydrogen gas in an acidic solution like HCl which comes before hydrogen. Okay. Point number three, the metal which comes before hydrogen, if it is introduced in an acidic solution of HNO3, at that point of time hydrogen gas is not produced. At that point of time nitrogen oxides are produced without the liberation of H2 gas. Okay, I hope this is clear. And one more point, the stability of your metal oxides. Stability of your metal oxides. It depends on the SOP, directly proportional to SOP. Or you can say inversely proportional to SRP. So that metal whose SRP will be more, the stability of its oxide will be less. The stability of its oxides will be less. So basically those metals which come before hydrogen, they have got lesser SRP. That means their oxides are comparatively more stable. And those metals which come after hydrogen, their oxides would be, their SRP is more. That means the stability of their oxide will be less. That is the reason why the oxides of all these metals which come after hydrogen, their oxides are highly unstable and they easily decompose on heating. Okay? Perfect. Now you need to just tell me one thing, guys. What is the answer of this question? I need a stability of these oxides. Stability of oxide is inversely proportional to SRP. Which one has got least SRP among copper, magnesium, zinc and lithium? Lithium has got the least SRP. So its oxide will be maximum stable. So I would say the stability of D is maximum. Right? Now among copper, magnesium and zinc, magnesium has got lesser SRP. Right? Among copper, magnesium and zinc. So magnesium comes here, zinc comes here, Copper comes here. So magnesium oxide would be more stable, then zinc oxide, then copper oxide. Magnesium oxide, zinc oxide, copper oxide. Right? Magnesium oxide, zinc oxide, copper oxide. This is the stability of these. If I am clear with all of this, tell me once in the chats quick. Yes? All clear? All clear, people? All right. Now, this particular topic, that is the most important topic of the chapter. Let's do this particular topic after a dinner break. So I'm giving you a dinner break of exactly 40 minutes. Okay. So I'm keeping the break. It is basically your dinner break till, what is the time? It is 8:32. So but I would want every one of you to be back on time, because something which I'm going to start now, that is the actual stuff which is asked in the exam. Okay? And I would want all of you to be back on time. Otherwise, there is no fun in teaching if you would sleep. Yeah? Okay? So be back on time, guys. Take care. I'll see you. So are you all back? Yes. Can you all hear me? All right, all right. So are you done with your dinner, everyone? Are you done with your dinner? Are you all done? To study equilibrium, you have to go for mole concept first. Okay? So study mole concept first, then you can go for equilibrium. Do not jump directly into equilibrium. And there is no need to spam now. I think you got your answer. All right, so tell me whatever things we discussed till now, is every single thing clear? Tell me, people, whatever things we discussed till now, is every single thing clear? Every one of you? Let me know quickly in the chats. Yes, I'm done with my dinner. All right, guys. So let's get going then. Let's get started with the most important topic of the chapter. And you know the topic. That is your Nernst equation. Okay? Nernst equation. And guys, since it's already been like 4 hours and 15 minutes, so let's do one thing. I'll break this particular chapter into 2 parts. Because as far as I can see, the way things are going in detailed manner, it won't be complete in 12 hours. Okay? All right? So in this particular session, let's complete the EMF part. In this particular session, let's complete the EMF part. And tomorrow morning at 9 a.m. or 10 a.m., I'll post the remaining 3 to 4 hours, okay, of this particular chapter, wherein I'll be doing the electrolysis part. I think that's going to be more convenient. Yeah? That is going to be more convenient. Sir, can I refer this video for boards? Well, honestly speaking, this session is not for boards. Okay? This is not for boards. So people, is it convenient then? In the today's session, let's complete the EMF part. That's also a huge part, EMF part, okay? And the remaining 3 to 4 hours, I'll be posting tomorrow morning at 10 a.m. on this channel. Today's session will take still like 2 to 3 hours. Yeah, not less than 3 hours. No, the part 2 I'll be posting in the recorded format. Part 2, the electrolysis part, that I'll be posting in the recorded format. Okay? Because tomorrow you have got one more live session on the channel taken by Ambika ma'am. So I don't want to clash with that. Okay, let's move on then. Nernst equation, my dear students. Let's first of all know what this Nernst equation is all about and from where do we get this. Try to understand what I'll be saying. I'm going to write an equation from thermodynamics. And the equation is delta G is equal to delta G naught plus RT ln of QC. This is one of the equations which I have written from the chapter Thermodynamics. Now from this equation itself, I am going to derive your actual Nernst equation, which you will be using in the questions. My dear students, first of all, you know your delta G. Delta G is nothing but minus NFE cell. Delta G naught is minus NFE naught cell plus RT ln of QC. Okay. If I divide throughout with minus NF, my dear students, this will become E cell is equal to E naught cell minus RT divided by NF, and this is ln of QC. Now let me do one thing. Let me write the logarithmic form of the same equation. So I'll say E cell is equal to E naught cell minus 2.303 RT divided by NF, and it's going to be log of QC. Well, this particular equation which I made over here, you call this particular equation as the Nernst equation. You call this particular equation as the Nernst equation. But my dear students, I'm not going to use this equation in the questions. I'm further going to simplify it. Let me further simplify it a bit. What simplification exactly? Let me do one thing. If I take the value of temperature as 25 degrees centigrade, that means 298 Kelvin. If I take the value of Faraday's constant as 96500 Coulomb, if I take the value of R as 8.314 joules per Kelvin per mole, if I put all these parameters into this equation, what do I get? I will be getting E cell is equal to E naught cell minus 0.0591 divided by N, and it's going to be log of QC. Okay, this equation is what you call as your Nernst equation. This is your Nernst equation. Now, my dear students, in this Nernst equation, what are these parameters which we have mentioned over here? Since QC you already know, that is the reaction quotient. I've already told you how to calculate this. N, number of moles of electrons exchanged. I've already told you how to calculate this. E naught cell, standard EMF of the cell, that is E naught cathode minus E naught anode. Already told how to calculate this. E cell will be the EMF of the cell under non-standard conditions. Okay? E cell would be EMF of the cell under non-standard conditions. Now, my dear students, where all do we use this Nernst equation? Where all do we use this Nernst equation? Remember, first of all, this Nernst equation is used to calculate. This Nernst equation is used to calculate the oxidation potential of the half cell. Half cell means electrode. This Nernst equation is used to calculate the oxidation potential of the half cell of the electrode under non-standard conditions. Under non-standard conditions. And how exactly you guys are going to write Nernst equation at that point of time when you will be supposed to calculate the oxidation potential? You'll write Nernst equation like this. Instead of E cell, you'll write EOX. Instead of E naught cell, you'll write E naught OX minus 0.0591 divided by N. Then it's going to be log of QC. This equation I'll be using when I will be supposed to calculate the oxidation potential of the half cell under non-standard conditions. Let me tell you, this EOX, it is nothing but it is the oxidation potential of what? Of the half cell. Under which conditions? Under non-standard conditions. Okay. What is this E naught OX? E naught OX represents standard oxidation potential of the half cell. This N already you know, it represents number of moles of electrons exchanged. Number of moles of electrons exchanged. And QC, all of you are already familiar with. What is that? That is the reaction quotient. So when we are supposed to calculate the oxidation potential of the half cell, oxidation potential of the electrode under non-standard conditions, I will write the Nernst equation in this format. Okay. Application number 1. Application number 2. If, for example, I'm supposed to calculate the reduction potential of the half cell means electrode, under which conditions? Again, under non-standard conditions. If I'm supposed to calculate the reduction potential of the half cell, again, under which conditions? Under non-standard conditions. So again, I'll be using the Nernst equation. How exactly I'll be using the Nernst equation? Instead of E cell, I'll write ERED. Instead of E naught cell, I'll be writing E naught RED minus 0.0591 divided by N, and it's going to be log of QC. Okay. This equation I'll be using where? Where do I use this particular equation? This equation is used to calculate the reduction potential of the half cell under non-standard conditions. So this is what we call as, this ERED is what we call as a reduction potential of the half cell under which conditions? Under non-standard conditions. This E naught RED is what you call as standard reduction potential. This N you already know, number of moles of electrons exchanged, right? And QC is nothing but reaction quotient. So application number 1, to calculate oxidation potential of the half cell. Application number 2, to calculate the reduction potential of the half cell. Now application number 3. Application number 3 is going to be to calculate the EMF of the cell. To calculate the EMF of a complete cell under which conditions? Under non-standard conditions. And when you are supposed to calculate EMF of a complete cell under non-standard conditions, at that point of time, the Nernst equation is written like this. E cell is equal to E naught cell minus 0.0591 divided by N, and it's log of QC. Log of QC. Okay. And this E cell is what you call as EMF of a cell under which conditions? Under non-standard conditions. This E naught cell is what you call as standard EMF of the cell. This is the standard EMF of the cell, which is nothing but E naught cathode minus E naught anode. And you already know number of moles of electrons exchanged. Number of moles of electrons exchanged in the net cell reaction. And QC is something which already you know. What is that? That is the reaction quotient. That is the reaction quotient. Now guys, let's try to exactly get into the details of the Nernst equation. So till now, I just gave you the Nernst equation, number 1. Number 2, I told you under what conditions we use the Nernst equation to calculate oxidation potential of the half cell, to calculate reduction potential of the half cell, and to calculate the EMF of a complete cell under non-standard conditions. These are its main 3 applications. Okay. Now we'll get to know how to write this Nernst equation one by one for half cells, for complete cells, for hydrogen electrodes, etc., etc. So try to understand what exactly I'm going to do. So mark the heading here as Nernst equation for the half cells. Nernst equation for the half cells. Mark this heading, guys. Okay. First of all, for example, you have got a container. This is the container, guys. In this particular container, for example, we have got Mn positive ions. We have got Mn positive ions. And with that, there are some anions as well. So basically, I have taken a salt here, and that salt got dissociated into cation and anions. Perfect. So in this solution, let me assume that there are equal number of cations and anions present. If there are equal number of cations and anions present, that means the solution right now is electrically neutral. Right? Now, my dear students, imagine that I'm introducing a rod made up of metal M. I've introduced a rod made up of metal M into a solution containing its own ions. So I've introduced a rod in a solution containing its own ions. So I'll be calling this particular setup as the electrode, right? This is the electrode, first of all. This is the electrode. Now, my dear students, you know, this electrode can behave like anode. It can behave like cathode as well. This electrode, it can behave like anode as well as cathode. So when this electrode behaves like the anode, what's going to happen? I would say at that point of time, oxidation is going to happen. When the electrode behaves like the anode, I would say oxidation is going to happen. What happens during oxidation? I would say metal solid will start getting converted into Mn positives. So reaction is going to be M solid getting converted into Mn positive aqueous, and with that you'll be writing N electrons. This is the reaction taking place when this particular electrode behaves like the anode. Okay. Now, my dear students, if I do one thing, if I write the expression for reaction quotient, you will have to start with the product. You'll write concentration of Mn positive raised by stoichiometric coefficient divided by, this is solid, nothing to do with this. Simple. Okay. How many moles of electrons are exchanged in the overall reaction? I would say N moles of electrons are exchanged. Perfect. Now, if I write the Nernst equation, I'll write Nernst equation like this. Since I made electrode to behave like anode, at anode oxidation takes place. So technically, I want to calculate the oxidation potential of this half cell under non-standard conditions. The oxidation potential of the half cell under non-standard conditions will be equal to E naught OX. That means the standard oxidation potential of the same cell minus 0.0591 divided by N log of QC. And QC is nothing but, QC is concentration of Mn positive. QC is nothing but, QC is concentration of Mn positive. Perfect. So this is, with the help of this particular equation, I can calculate the oxidation potential of this electrode. Under which conditions? Under non-standard conditions. You just have to put the value of concentration of Mn positive in the solution, N value, standard oxidation potential, solve this, get the oxidation potential. Right? Now, guys, understand one more thing. See, imagine that the electrolyte which you have taken in this container, imagine that the concentration of electrolyte in the container in the beginning is more the concentration of electrolyte in the container, that means more would be the number of Mn positives in the container. The electrolyte which you have kept in the container in the beginning, if its concentration is more, that means more will be the number of Mn positives in the container. If the number of Mn positives in the container are more, that means this term, its value would be more. If the value of this term is more, that means the difference between these two will be less, which means that oxidation potential of the half cell would be less. So I would say oxidation potential of the half cell, oxidation potential of the electrode is inversely proportional to concentration of electrolyte present in the container. This is one important conclusion which I would want every one of you to remember. Oxidation potential of the electrode is inversely proportional to the concentration of electrolyte in the container. What does that mean? That simply means something like this. For example, this is zinc sulfate in the container. For example, here also you have got zinc sulfate in the container. Here you have introduced zinc rod. Here you have also introduced a zinc rod. Let's say concentration of zinc sulfate here is 10 molar. Let's say concentration of zinc sulfate here is 100 molar. Okay. So, do we have same electrodes? Absolutely, we have same electrodes. Where the difference lies? The difference lies in the concentration of electrolyte. So, wherever the concentration of electrolyte would be more, oxidation potential will be less. So, I would say, over here, the concentration of electrolyte is more in this container. So, the oxidation potential of this half cell, oxidation potential of this electrode will be comparatively less than that of this one. Okay? I believe this is properly clear to everyone. Now, my dear students, one more thing. There could have been one more possibility that this electrode could have behaved like the cathode. This electrode It could have behaved like what? It could have behaved like the cathode. Now you tell me, when the same electrode behaves like the cathode, what's going to happen? Oxidation or reduction? When the same electrode behaves like the cathode, I would say reduction is going to happen. Reduction means gain of electrons. So Mn positives in the solution, they are going to collide with the rod. So I would say Mn positive ions in the solution, they will collide with the rod. They will take N electrons from the rod and will get converted into M solid. Okay. Now, if I write the QC expression, QC is going to be start with the product. It's in solid form. So 1 divided by concentration of Mn positive. Raised power stoichiometric coefficient, that is 1. Now, my dear students, since you made this electrode to behave like cathode, and at cathode reduction takes place. So technically, what do I want? I want to calculate the reduction potential of the half cell. I want to calculate the reduction potential of this electrode, which will be equal to, as per Nernst equation, E naught RED minus 0.0591 divided by N, and it's log of QC. QC is nothing but 1 upon concentration of Mn positive. 1 upon concentration of Mn positive. Okay. 1 upon concentration of Mn positive. Guys, if you understand carefully, if I say, what if the concentration of electrolyte in the container is more? If the concentration of electrolyte in the container is kept more, that means the concentration of Mn positives in the container will be more. If the concentration of Mn positives in the container is more, that means 1 divided by concentration of Mn positive. If the concentration of Mn positive is more, so 1 divided by this value would be less. If this value is less, if this value is less, if this value is less, that means this entire value will be less. If this entire value will be less, that means the difference between these two would be more. So which technically means your reduction potential would be more. So reduction potential and the concentration of electrolyte, do you see directly or inversely? They are directly proportional. So I would say the reduction potential of the electrode, reduction potential of the half cell, that is directly proportional to the concentration of electrolyte present in the container. So more the concentration of electrolyte present in the container, more is going to be the reduction potential of the electrode. This is one important conclusion, guys. Yeah? Am I clear with this? Everyone, people, am I clear with this? Am I clear with this, people? Everyone. Right? Now, let's get to know how the same Nernst equation is written for the hydrogen electrode. So I'm marking the heading as Nernst equation for hydrogen electrode. Nernst equation for hydrogen electrode. Nernst equation for hydrogen electrode. Let's try to understand what it means. See, guys. For example, I have taken a hydrogen electrode here. And I believe all of you remember how hydrogen electrode is made. But I'm not going into the details of that again. So let me just roughly make the hydrogen electrode. Let's say this is the container. And this particular container contains H positive ions here. Okay. And here you have got hydrogen rod. Rest you know how this hydrogen rod is made. Let's say the pressure of the hydrogen here is, for example, 1 atm. I believe all of you remember how this hydrogen electrode is made with the help of platinum. So first of all, the hydrogen electrode which I've taken here, even this hydrogen electrode, it can behave like anode or it can behave like cathode. So first of all, let's do one thing. Let's make this hydrogen electrode to behave like anode. When this hydrogen electrode behaves like anode, what's going to happen? You know, at anode, oxidation is going to take place. So if this hydrogen electrode behaves like anode, I would say it will undergo oxidation. And when the hydrogen electrode undergoes oxidation, what will be the reaction? I would say H2 gas would get converted into twice H positive. And with that, you'll be writing 2 electrons. Okay. This is the reaction when this hydrogen electrode is going to behave like the anode. Okay. Now, my dear students, how many moles of electrons do you see here? 2. That means N value here is equal to 2. Okay. If I want to write the QC expression is going to be concentration of H positive raised power stoichiometric coefficient 2 divided by partial pressure of H2 gas. And the pressure of H2 gas I have kept as 1 atm. So QC is nothing but that's concentration of H positive raised power 2. Now people, since I made this electrode to behave like anode and at anode oxidation takes place, so technically I wanted to calculate oxidation potential of this electrode, which is nothing but E0OX minus 0.0591 divided by N log of QC. I hope you remember the standard oxidation potential as well as standard reduction potential of hydrogen electrode is taken to be 0. We have discussed that. So this term is already equal to what? This term is already equal to 0. If this term is 0, it is going to be minus 0.0591 divided by N values 2 log of QC. QC is concentration of H positive raised power stoichiometric coefficient, that is 2. So I would say oxidation potential of the hydrogen electrode is equal to minus 0.0591 divided by 2 log of M raised power N is N log M. So 2 comes to the front, 2 gets cancelled out. When 2 gets cancelled out, what am I left with? I'm left with only log of H positive concentration. Okay. If I do one more thing, I can write EOX is equal to 0.0591. If I take minus in the bracket, it becomes minus log of H positive, right? And you know, my dear students, it will be 0.0591 minus log of H positive is nothing called as pH. Minus log of H positive is nothing but it is called as the pH. So, oxidation potential of the hydrogen electrode. Oxidation potential of the hydrogen electrode when the pressure of hydrogen gas is kept 1 atm is equal to 0.0591 multiplied by the pH of this particular solution which is here in the container. Am I clear with this? I believe this is clear. Similarly, my dear students, if you want to derive an expression for the reduction potential, of the same hydrogen electrode, it will be simply just change the sign. It would be minus 0.0591 multiplied with pH of the solution. Okay, this is the reduction potential of the hydrogen electrode. Perfect. When the pressure of the gas is kept as 1 atm. Am I clear with this? And if I'm clear with this, let's try to use all these concepts in the questions directly. Let's try to use all these concepts in the questions so that you'll understand where all do we use all this stuff. Look at this question, guys. Look at this question. Calculate the oxidation potential of the following half cell. For the following half cell. If you look carefully, in the container you have FeSO4. Right? And in this FeSO4 solution, you have introduced an iron rod. Okay? So I would say you have basically taken a container and in this particular container you have kept FeSO4. This FeSO4 in the container would have dissociated as Fe di positive and SO4 di negative. Now you have introduced iron rod here. So I would say I've introduced iron rod in a solution containing its own ions. Okay, so this is an electrode, an iron electrode. I will have to calculate its oxidation potential. If I want to calculate the oxidation potential of this iron electrode, you know oxidation takes place at anode. So I'll make sure this electrode behaves like the anode. And when this electrode behaves like the anode, what's going to happen? When this electrode is going to behave like an anode, oxidation is going to take place. See, it is 0. This is plus 2. 0 to plus 2. Increase. Increase means oxidation, loss of electrons. So reaction is going to be Fe solid will be getting converted into Fe di positive aqueous. With that, you'll be writing 2 electrons. This is going to be the reaction at anode. Perfect. Now, what is the N value first of all? N value here is 2. What is the QC value? QC is going to be concentration of Fe di positive raised power stoichiometric coefficient, that's 1. Yeah. Now, what is the concentration of Fe di positive in the solution? Look carefully. Initially, at time t is equal to 0, what was the concentration of FeSO4? That was 0.1 molar. This would be 0. This would be 0. Now imagine this has got completely ionized. It has got completely dissociated into its ions. So I'll be left with nothing. 1 mole gives 1, 0.1 would have given 0.1. This would be also 0.1 molar. So I can say concentration of Fe dye positive in the solution is 0.1 molar. 0.1 means 10 raised power minus 1. So this is the value of QC. I got the value of QC, I got the value of N. Now what do we have to calculate? I have to calculate oxidation potential. So I just have to use the Nernst equation. I can say oxidation potential of the half cell is equal to E naught OX, standard oxidation potential, minus 0.0591 divided by N and its log of QC. Now my dear students, EOX is equal to, what is the SOP value? Is the SOP value given? Check it out. This is plus 2 to 0. Plus 2 to 0, decrease. Decrease means reduction. So this is your SRP. But what do I need? I need SOP here. I need SOP here. So just change the sign. The sign is going to be plus 0.44 minus 0.0591 divided by N value. What is the N value? What is the N value? N value here is 2 and it's going to be log of QC. QC is 10 raised power minus 1. So you can finally write it as 0.44 minus 0.0591 divided by 2. Log of M raised power N is N log M. So minus 1 comes to the front. Log 10 is 1. Just solve this and get the answer in volts. So this is going to give you the oxidation potential of this particular electrode, right, which I was supposed to calculate. If I am clear, let me know in the chats. Yeah? Let me know quickly in the chats if this particular question is clear. My dear students, now whatever value will be coming after solving this equation, whatever value will be coming, you just have to change the sign of that value. You just have to change the sign. What would you get? You would be getting the reduction potential of the same electrode. Yeah? People are saying the answer is coming out to be 0.47. So if it is 0.47 volt, so this is the oxidation potential of the electrode. So I would say if you were supposed to calculate the reduction potential of the same electrode, that would have been minus 0.47 volt. As simple as that. Right? Perfect. Let's move on to one more question. Look at this question, guys. Calculate the oxidation potential of the following half cell. Again, you are given with the half cell. Half cell means electrode. Again, you are given with the electrode. And if you look carefully, this is hydrogen electrode. And you are supposed to calculate its oxidation potential. You are supposed to calculate its oxidation potential. If the pressure was 1 atm, then you would have used the direct result which I gave you a few minutes back. EOX is equal to 0.0591 into pH. But right now you cannot use that result because that result is valid only when the pressure of hydrogen gas is 1 atm. Right? But here the pressure of hydrogen gas is 10 atm. So what do we do in this case? We have to calculate the oxidation potential. If we need to calculate the oxidation potential, that means we'll make sure that the electrode behaves like the anode. And when it behaves like the anode, what would be the reaction? The reaction would be H2 gas gives 2 times H positive aqueous, and with that you'll be writing 2 electrons. Okay. So what is the N value first of all? N value is 2. What is the QC value? QC is going to be concentration of H positive raised power stoichiometric coefficient divided by pressure of H2 gas. Now, if I ask you what is the concentration of H positive? Concentration of H positive is 10 raised power minus 1 molar raised power 2 divided by pressure of H2 is 10. So the value comes out to be 10 raised power minus 3. So this is QC. This is QC. Okay. You got the QC value, you got the N value. What we have to calculate? Oxidation potential. So I would say oxidation potential of the half cell is equal to E naught OX minus 0.0591 divided by N and its log of QC. Now people, EOX is equal to E naught OX. For hydrogen electrode, SOP value is 0. So this is 0 minus 0.0591. N value we have calculated as 2. Log of QC. QC value is how much? QC value is 10 raised power minus 3. Right? So it becomes minus 0.0591 divided by 2. log of m raised power n, which is n log m. So minus 3 comes to the front, log 10 is 1. So this answer will come in volts. Correct? I hope this is clear till here. Right, people? Look at this particular question. Look at this particular question. A solution containing 4 into 10 raised power minus 4 molar Cr2O7 dinegative and 2 into 10 raised power minus 2 molar Cr tripositive ions shows a pH of 1. Calculate the reduction potential of the half cell. We have to calculate the reduction potential of the half cell. The half cell that's given to us is basically like this. We are directly given the reaction of the half cell, Cr2O7 dinegative is getting converted into Cr tripositive. So first of all, if you want to show the half cell you can show like this. Platinum solid, Cr2O7 dinegative aqueous, comma Cr tripositive aqueous. This is your half cell first of all. You are supposed to calculate its what? You are supposed to calculate its reduction potential. You are supposed to calculate its reduction potential. If you are supposed to calculate its reduction potential, that means you are supposed to make sure that this electrode behaves like the cathode, because at cathode only reduction takes place. Now, when this electrode behaves like the cathode, reduction is going to take place. Now have a look. Oxidation state of chromium here is +6. Here chromium is in +3. So +6 to +3, decrease means reduction, gain of electrons. So the reaction is going to be, the reduction reaction is going to be Cr2O7 dinegative will be definitely gaining some electrons and getting converted into Cr tripositive. Now first of all, on this side we have got 2 chromium, so I'll make it as 2 chromium. So how many electrons are being gained here? Say +6 to +3. +6 to +3. Change in the oxidation state is 3. 3 is the change for one atom. I have 2. So 3 2s are 6. So Cr2O7 dinegative plus 6 electrons gives 2 times Cr tripositive. If I ask you, is this the complete reaction? This is still not the complete reaction. Why is that? Because no doubt you have balanced chromium, but have you balanced oxygen? You have not balanced oxygen. So on left side, you have got 7 oxygen. So on right side, you'll be adding 7 water molecules. Now, on right side, you have got 7 to 14 hydrogens. So I'll be adding 14 H positives on this side. Already I've told you how do we balance oxygen and hydrogen. We have studied that. Right? Now people, there are 6 moles of electrons here. So N value is nothing but 6. We got the value of N. Correct? We got the value of N. Now since I have to calculate the reduction potential. So N we got. What is left? Reaction quotient is left. To calculate the reaction quotient value, I'll be starting with the product. So it's concentration of Cr tripositive raised power 2. This water is a liquid state, so nothing to do with that. Divided by. Come to the reactant side. So first of all, it's going to be concentration of H positive raised power 14. Right? Concentration of Cr2O7 dinegative raised power stoichiometric coefficient, that's 1. Perfect. So this is the QC value. Now, as far as the question is concerned, what is the concentration of Cr tripositive? Concentration of Cr tripositive is given to me as 2 into 10 raised power minus 2. Raised power stoichiometric coefficient, that's 2. Divided by. What is the H positive concentration? Well, H positive concentration is not given to me. But if you look carefully, we are given with the pH. If pH is equal to 1, that means H positive concentration would be equal to 10 raised power minus 1 molar. Simple. So H positive concentration is nothing but 10 raised power minus 1 and raised power 14. What is the concentration of Cr2O7 dinegative? It is given to me in the question as 4 into 10 raised power minus 4. So this term gets cancelled. So the value comes out to be 10 raised power 14. So this is the QC value. I got the QC value. I got the N value. And look at this value. E0 is given. Now, is this SOP or SRP? See, +6 to +3, decrease means reduction. So this is SRP. This is basically SRP that is given to me. What am I supposed to calculate as far as the question is concerned? I'm supposed to calculate the reduction potential. I'm supposed to calculate the reduction potential. Now people, if you want to calculate the reduction potential, then you have to write the Nernst equation. E RED is equal to, it's going to be E naught RED minus 0.0591 divided by N, and it's going to be log of what? Log of QC. So E naught RED. is the standard reduction potential, SRP, that's given to me as 1.5 minus 0.0591 divided by, what is the N value? N value is nothing but 6 and log of QC. QC is 10 raised power 14. Now it is just a matter of calculation and you'll be getting the answer in volts. That's all. Is it clear, people? Tell me once in the chats if this is clear. Everyone. Tell me once in the chats if all of this is clear. Everyone. Perfect, guys. So moving on to one more question. Look at this question carefully. Look at this question. We are given with the reaction, we have to calculate the reduction potential in neutral solution. Neutral solution means pH will be 7. Yeah? So what do we do? How do we solve this question? Then still now, whatever questions we solved, in none of the question, the reaction was given to us. Every time I was supposed to make the reaction. But this is the question wherein the reaction is already given. So you're not supposed to make the reaction. The reaction is already given. Okay? How many electrons do you see? 1. So N value is 1. So if you write the reaction quotient, start with the product. It's pressure of NO2 because it's in gaseous phase. Raised power stoichiometric coefficient 1. Water is in liquid state, nothing to do with that. NO3 negative in aqueous state. So concentration of NO3 negative. Raised power stoichiometric coefficient 1. This is concentration of H positive. Raised power stoichiometric coefficient 2. That's all. Now guys, we are almost done. We are almost done. How exactly? pH is equal to 7. If pH is equal to 7, that means the concentration of H positive is going to be 10 raised power minus 7 mole. 10 raised power minus 7 mole. Now, what is the pressure of NO2 that's given to me? 1 bar divided by NO3 negative concentration is 1 molar. H positive concentration is 10 raised power minus 7. 10 raised power minus 7 ka square comes out to be 10 raised power minus 14. So the overall value will be 10 raised power 14. So I got QC, I got N. What do I have to calculate? What do I have to calculate? I have to calculate the reduction potential. In order to calculate the reduction potential, you'll write the Nernst equation. E RED is equal to E naught RED minus 0.0591 divided by N, and it's going to be log of what? Log of QC. Now people, what is this E naught RED? This is the standard reduction potential. And standard reduction potential of the half cell is given to me as 0.78 minus 0.0591. N value is given to us in the question, that is 1. Log of QC. QC is 10 raised per what? 10 raised per 14, right? Now it is just again the matter of calculation. So this is 0.0591. Log of m raised per n is n log m. So 14 log 10 is 1. Just solve this particular term and get the answer in volts. Simple. So this will give me the reduction potential of this half cell. Right? I believe it's clear. Similarly, let's try to solve this particular question. Let's try to solve this particular question. Look at this question, guys. The question is calculate the reduction potential at pH equal to 14. At pH equal to 14 for the electrode, that is copper electrode at 25 degrees centigrade. KSP of CuOH whole twice is given. Okay. E naught value is also given. So how do we exactly approach this sort of a question? The electrode that's given to us is copper electrode, right? And what are we supposed to calculate? We are supposed to calculate the reduction potential. So in order to calculate the reduction potential, I'll have to make sure the electrode behaves like the cathode, because at cathode only reduction takes place. So when the electrode behaves like the cathode, a reduction is going to take place. Reduction means copper dye positive would be gaining 2 electrons and would be getting converted into copper solid. Okay. What is the N value here? N value here is 2. What is the QC value here? QC value will be 1 divided by concentration of copper dye positive. This is solid. Its active mass is 1 divided by concentration of copper dye positive here. Now people look carefully. In the question, am I given with copper dye positive concentration? No, not anywhere. I'm not given with the copper dye positive concentration. I have to calculate the copper dye positive concentration. How exactly? For that purpose, if you look carefully, Ksp of CuOH whole twice is given. So first of all, CuOH whole twice. CuOH whole twice. How will it dissociate? Copper di positive plus 2 times OH negative. If you would want to write the Ksp expression is simply going to be concentration of copper di positive raised power 1, concentration of OH negative raised power 2, right? Now, what do I actually need? Actually, I need copper di positive concentration. So to calculate copper di positive concentration, I need Ksp value, I need OH negative concentration. Ksp value is given, but OH negative concentration is not given. So how do I calculate OH negative concentration now? How do I calculate OH negative concentration now? OH negative concentration can be calculated with the help of this particular term. pH. pH in the question is given to me as 14. If pH is equal to 14, since you know at 25 degrees centigrade, pH plus pOH is equal to 14. So if pH is equal to 14, so pOH will be 14 minus 14, 0. If pOH is 0, that means OH negative concentration will be 10 raised power minus 0. That means 10 raised power 0, which comes out to be 1 molar. I got the OH negative concentration. If I got the OH negative concentration, Ksp value in the question is given. 10 raised power minus 19 is equal to, this is concentration of copper di positive. OH negative concentration is 1. So I got the concentration of copper di positive as, I got the concentration of copper di positive as 10 raised power minus 19 molar. So Qc value came out to be 10 raised power plus 19. If you got the Qc, what do we have to calculate? We have to calculate the reduction potential. So in order to calculate the reduction potential, use the Nernst equation. ERED is equal to E naught RED minus 0.0591 divided by N, and it's a log of what? Log of Qc. So my dear students, E naught RED, standard reduction potential, that is given to me in the question, that is 0.34 minus 0.0591 divided by, what is the value of N? N value is 2. Log of Qc. Qc value is 10 raised per what? 10 raised per 19. Now just the matter of calculation. 0.34 minus 0.0591 divided by 2. Log of m raised per n is n log m. So 19 comes to the front. Log 10 is 1. Again, just the matter of calculation. And you will be calculating, you'll be getting what? You'll be getting the reduction potential of the electrode, which I was supposed to calculate. If I'm clear with this, tell me once in the chats quick. Quickly, guys. Done? They can ask oxidation potential as well. If they ask oxidation potential, then reverse the reaction. That's it. Then reverse the reaction. Oh, is it cyclone in Tamil Nadu? Is there a cyclone? Okay, just stay safe. All right, guys. Chalo, look at this particular question. Look at this one. Look at this one, guys. The pressure of hydrogen required to make, potential. Potential means a reduction potential. Required to make a reduction potential of hydrogen electrode 0. So basically in the question, we have to make the reduction potential of hydrogen electrode 0 in pure water. We have to make the reduction potential of hydrogen electrode as 0 in pure water. And for that purpose, in order to make the reduction potential of hydrogen electrode 0, what should be the pressure of hydrogen gas? That is the question. That is the question. That is the question. Now, how do we solve this particular question? First of all, if you look at the hydrogen electrode, do you remember how hydrogen electrode is made? These are the H positives kept. And this used to be the inverted tube. This used to be the platinum wire. Over here, H2 gas used to be introduced. Okay. So basically, we have to calculate the pressure of H2 gas. The pressure of H2 gas required to make the reduction potential of hydrogen electrode as 0. Now, in order to make the reduction potential of hydrogen electrode as 0, let's do one thing. Let's make sure that hydrogen electrode behaves like the cathode first. When it behaves like the cathode, the reaction is going to be 2 times H positive aqueous plus 2 electrons gives what? Gives H2 gas. This is the reaction which is going to take place first. Okay, this is the reaction which is going to take place. Now, N value is how much? N value is 2. If N is 2, write the QC expression. QC is going to be pressure of H2 raised power 1 divided by concentration of H positive raised power 2. Pressure of H2 I have to calculate. Divided by, what is the concentration of H positive? They mentioned pure water. Pure water at 25 degrees centigrade. What is the pH of pure water? What is the pH of pure water at 27 degrees centigrade? Sorry, at 25 degrees centigrade. That's 7. Because water is neutral. So concentration of H positive will be equal to 10 raised power minus 7 molar. So technically concentration of H positive is given 10 power minus 7. So its square comes out to be 10 raised power minus 40. This is QC. You got the QC value. You got the N value. Now as per the question, use the Nernst equation. I can say ERED, reduction potential of the hydrogen electrode, is equal E naught RED, standard height SRP, minus 0.0591, divided by what? Divided by N, log of what? Log of QC. And QC value is pressure of H2 divided by 10 raised power minus 14. Now, this is SRP of hydrogen electrode, that is 0 already. Because you know SOP as well as SRP of hydrogen electrode is 0. Now, as per the question, we have to make the reduction potential of hydrogen electrode 0 as well. So this is 0, this is 0. This means that log of partial pressure of H2 divided by 10 raised power minus 14. This value has to be 0. When is log of x 0? Log of x is 0 only when x is equal to 1. Log of x is 0 when x is equal to 1. So x here is partial pressure of H2 divided by 10 raised power minus 14. This value has to be 1. It means that partial pressure of H2 is equal to 10 raised power minus 14. Let's say the units are in ATM. So I would say the pressure of H2 gas should be 10 raised power minus 14 ATM. The pressure of H2 gas should be 10 raised power minus 14 ATM. Then only the reduction potential of this electrode, then only the reduction potential of this half cell would be 0. Am I clear with this? Did you understand how to deal with such kind of the question? Did you understand, guys? Look at this one. Look at this particular question, guys. Who was this polar? Who was this polar? Yeah? Okay. The question is zinc electrode is dipped in a 0.1 molar solution of its salt at 25 degrees centigrade. Assume the electrolyte is 20% dissociated. Calculate the electrode potential. Electrode potential means the reduction potential. If in the question they ask you to calculate the electrode potential, that means you are supposed to calculate what? Reduction potential. See guys what the question says. Try to understand. It's a simple basic question only, not difficult. Okay. Imagine you have got a container. Imagine you have got a container. In this container, you are keeping a salt of zinc. You are keeping a salt of zinc. For example, you are keeping zinc sulfate. This is the salt of zinc. Now this zinc sulfate, how it should undergo dissociation? Zinc di positive plus SO4 di negative. Now you are keeping zinc rod here in the solution. So basically you got an electrode. Which electrode this is? This is zinc electrode. So you have got a zinc electrode. Now we have to calculate the reduction potential of the zinc electrode when 20%, is it mentioned 20%? Yes. When 20% zinc sulfate dissociates into its ions. So when 20% of zinc sulfate would have dissociated into its ions, at that moment, at that point of time, what would be the reduction potential of the electrode? That is the question. Now, first of all, initially, what is the concentration of zinc sulfate I have taken? Concentration of zinc sulfate in the container initially was 0.1 molar. So this would be 0, this would be 0. Now, in the question they have mentioned that 20% zinc sulfate is dissociated. If 20% zinc sulfate is dissociated, that means alpha value, degree of dissociation, will be 20 by 100, that means 0.2. So I would say, when 20% zinc sulfate is dissociated, how much will be left? This would be C minus C alpha, this would be C alpha, this would be C alpha. So concentration of zinc dye positive when 20% electrolyte is dissociated. Concentration of zinc dye positive when 20% electrolyte is dissociated is equal to C into alpha. C value is 0.1 and your alpha value is 0.2. The value comes out to be 0.02. This is the concentration of zinc dye positive in the solution when 20% electrolyte would have dissociated. When 20% electrolyte would have dissociated, this would have been the concentration of zinc dye positive at that point of time. Now, what do we have to calculate? We have to calculate the reduction potential of the electrode when 20% electrolyte is dissociated. Now, in order to calculate the reduction potential, I have to make sure that the electrode behaves like the cathode, because at cathode only reduction takes place. And when this zinc electrode behaves like the cathode, what's going to happen? When this zinc electrode behaves like the cathode, what is going to happen? A reduction. So I would say zinc dye positives in the solution, they are going to collide with the rod. They will take 2 electrons from the rod and will get converted into zinc solid. This would be the reaction when this electrode behaves like the cathode, because at cathode reduction takes place. Right? Now, people, what is the value of N here? The value of N here is 2. That means 2 moles of electrons are exchanged. If I ask you the QC value, QC is going to be, start with the product, it's in solid state, so 1 divided by, it's going to be concentration of zinc dye positive. Now, what is the concentration of zinc dye positive? When 20% electrolyte is dissociated, that is 0.02. So it comes out to be 2 by 100, that means 50. So QC value came out to be 50. Yeah? QC value is equal to 50. If QC is equal to 50, what was I supposed to calculate? I was supposed to get the reduction potential of the electrode. And the reduction potential of the electrode is nothing but, it is E naught RED minus 0.0591 divided by N, and it's log of what? Log of QC. So what is E naught RED? This is what you call as SRP. See, plus 2 to 0. Plus 2 to 0 means decrease, reduction. So this is SRP already, which is given to me. Minus 0.76 minus 0.0591. N value here is 2. Log of QC. QC is 50. 50 can be written as 5 into 10. Now again a matter of calculation. So this will be minus 0.76 minus 0.0591 divided by 2. Log of M into N is log M plus log N. So log 5 plus log 10. Log 5 is 0.69 and log 10 is 1. So this entire value comes out to be 1.69. This entire value comes out to be 1.69. Now, again, just the matter of calculation, you just have to solve this and get the reduction potential of the half cell. So I believe you got to know how do we calculate the oxidation potential as well as the reduction potential of the half cell of the electrode under non-standard conditions. If this is clear, tell me once in the chats, then I'll move on to the Nernst equation for complete cells. Quickly, guys. Tell me quickly in the chats. Done? All right. Now let's move on to one more thing. What is that? That is the Nernst equation for complete cells. Nernst equation for complete cells. Okay. So first of all, when we are supposed to calculate EMF of a complete cell, first of all, a complete cell is made up of 2 half cells. A complete cell is made up of 2 electrodes, right? Whenever you are supposed to calculate EMF of a complete cell under non-standard conditions, at that point of time, you can use the Nernst equation. And how Nernst equation is used at that time? you can use this particular equation directly. E cell is equal to E naught cell minus 0.0591 divided by N log of QC. This is how you write the Nernst equation at that point of time. When you are supposed to calculate what? When you are supposed to calculate the EMF of a complete cell. When you are supposed to calculate EMF of a complete cell under non-standard conditions. Now let's get to know how do we use this exactly. For example, let me make one general question. A simple question I'm making here. The question is like this. I'm making a complete cell zinc solid, zinc dye positive aqueous, whose concentration is 0.1 molar. In the middle, I'm keeping salt bridge. On the right side, I'm keeping copper dye positive concentration, copper dye positive aqueous, whose concentration again I'm keeping 0.1 molar. And this is, for example, copper solid. Okay. Now, imagine E naught of zinc gives zinc dye positive is equal to 0.76 volt. Imagine E naught of copper dye positive gives copper is equal to 0.34 volt. I'm asking you to calculate the EMF of the cell. I'm asking you to calculate the EMF of the cell. Yeah? I'm asking you to calculate the EMF of the cell. How we are going to solve this sort of a question in which you are supposed to calculate EMF of a complete cell? My dear students, the process is really simple. First of all, these two lines, they represent the salt bridge. On the left side of the salt bridge, what do we have? We have anode. On the left side of the salt bridge, what do we have? We have anode. And at anode, what happens? Oxidation. At anode, as you can see, zinc gets converted to zinc dye positive. So 0 to plus 2. Increase. Increase means oxidation, loss of electrons. So at anode, I must say, your zinc solid is getting converted into zinc dye positive aqueous plus how many electrons? Plus 2 electrons. Right? This is the reaction taking place at anode. Yeah? Now, my dear students, N value. Sorry. This is the reaction takes place at anode. Now, what is the reaction taking place at cathode? At cathode, if you see, a reduction is taking place. Copper dye positive is getting converted into copper. So I would say copper dye positive aqueous would be gaining 2 electrons and then would be getting converted into copper solid. Now, if I ask you, are the electrons balanced in both the reactions? Yes, the electrons are balanced. If the electrons are balanced, you can add the two reactions. When you add the two reactions, the net reaction becomes zinc solid plus copper dye positive aqueous. It gives zinc dye positive aqueous plus copper solid. So N value here is 2. N value here is 2. Got it? N value here is 2. Yeah? N value here is 2. Now, if N is 2, if I get the QC value, QC is going to be concentration of zinc dye positive raised per stoichiometric coefficient 1 divided by concentration of copper dye positive raised per stoichiometric coefficient 1. What is the concentration of zinc dye positive? 0.1. What is the concentration of copper dye positive? 0.1. The value comes out to be 1. So QC value is equal to 1. Okay. QC value is equal to 1. Now, I got the QC, I got the N. I can calculate E naught cell as well. And you know E naught cell is nothing but E naught cathode minus E naught anode. So it is SRP of cathode minus SRP of anode. Now, this is your cathode. SRP of cathode, SRP of zinc. Well, this is SOP of zinc. What do I need? I need SRP of zinc. So minus 0.76. Minus SRP of anode. Sorry, I made a mistake here. This is basically SRP of cathode. SRP of cathode means SRP of copper. This is anode, this is cathode. So SRP of copper. SRP of cathode, SRP of copper. SRP of copper is given to me as 0.34. Minus SRP of zinc is minus 0.76. The value comes out to be 1.1 volt. So you got E naught cell, you got the value of QC, you got the value of N. Now you can directly use the Nernst equation. You can directly use the Nernst equation. You can say E cell is equal to E naught cell minus 0.0591 divided by N log of QC. Now in the question we got to know QC value is equal to 1. If QC value is equal to 1, that means log of 1 is equal to 0. This entire term becomes 0. So I would say E cell is nothing but E naught cell, and E naught cell we have already calculated. How much that is? 1.1 volt. This is something I was supposed to calculate. Yeah? Am I clear? Did you understand how Nernst equation is used for the complete cells? Did you understand how Nernst equation is used for the complete cells, people? Everybody? Let's solve a few more questions so that things are going to be like very smooth, very clear to you. Again, the similar type of question, which I believe you can easily solve. Again, the similar type of question, which I believe you can easily solve. We again have to calculate EMF of the cell. Now, in order to calculate EMF of the cell, what do I need to do? The same process which I have been following till now. What is the process? On the left side of the solid bridge, we write anode. At anode, what happens? Oxidation. Tin gets converted into SN dye positive. So I would say the reaction is going to be SN solid gives SN dye positive aqueous plus 2 electrons. This is the reaction at anode. Similarly, what would be the reaction at cathode? Pb dye positive is getting converted into Pb. So the reaction has to be Pb dye positive aqueous would be gaining 2 electrons and would be getting converted into Pb solid. This is the reaction at cathode. You got the reaction at anode, you got the reaction at cathode. Now add the two reactions because electrons are balanced, right? So I would say 2 electrons would get cancelled. So N is equal to 2. My net reaction becomes Sn solid plus Pb dye positive aqueous. It gives Sn dye positive aqueous plus Pb solid. This is my net reaction. If this is my net reaction, now what we can do? We can get the QC expression. QC is going to be concentration of Sn dye positive raised power stoichiometric coefficient 1 divided by concentration of Pb dye positive raised power stoichiometric coefficient 1, because this is in solid, nothing to do with them. Now what is the concentration of Sn dye positive? Concentration of Sn dye positive is 1 molar divided by concentration of Pb dye positive, that is 10 raised power minus 3. The value comes out to be 10 raised power 3 only. So QC you got the N value. Now comes your E0 cell. So how do I calculate E0 cell? E0 cell is again the same. That is E0 cathode minus E0 anode. E0 cathode means SRP of cathode. Cathode is your lead and SRP of lead is given. This is SRP. Pb dye positive Pb plus 2 to 0. Decrease means reduction. So this is SRP. So minus 0.13 minus SRP of anode, SRP of tin. SRP of tin is also given. That is also minus 0.14. The value comes out to be 0.01. Okay, this is E0 cell. Now E0 you know, QC you know, N value you know. Put all the values in the Nernst equation. Your Nernst equation is simple. That is E cell is equal to E0 cell minus 0.0591 divided by N. And it's going to be log of what? Log of QC. Now my dear students, E0 cell value we have calculated 0.01 minus 0.0591. N value we already got, that is 2. Log of QC. QC is how much? QC is 10 raised power 3. So again, just the matter of calculation. So this is 0.0591 divided by 2. Log of m raised power n is n log m. So 3 comes to the front, log 10 is 1. Again, the matter of calculation, get the answer in volt. Right? Am I clear, people? Am I clear till here? Everyone? All right. One more question and after that I'll be giving you a break. Okay, one more question and with that I'll be giving a break. Look at this question, guys. Look at this question. The reaction is given to us. The question says if E cell is equal to E0 cell at 25 degrees centigrade, concentration of Fe dye positive is this much, partial pressure of O2 is this much, pH is X, calculate X. That is the question. That is the question. Now, first of all, since the reaction is given, can I write the QC expression? Because the reaction is given. Otherwise, I was Till now, I was making the reactions. But here in this question, the reaction is already given. So QC is going to be, start with the product. So it's going to be concentration of Fe tripositive raised power stoichiometric coefficient 2, right? This water is in liquid state, so nothing to do with that, divided by. This is in solid state, nothing to do with that. I'll write partial pressure of O2 raised power 1 and concentration of H positive raised power stoichiometric coefficient 4, right? Now, as far as the question is concerned, pH is equal to X. If pH is equal to X, that means concentration of H positive would be 10 raised power minus 6 molar. Concentration of H positive would be 10 raised power minus 6 molar. Now, in the question, what is the Fe tripositive concentration? How much is Fe tripositive concentration? Sorry, this is Fe tripositive. This is not dipositive, this is tripositive, okay? My bad. Fe tripositive concentration is given to me as 10 raised power minus 3, because square comes out to be 10 raised power minus 6, divided by. Pressure of O2 gas is given to me as 10 raised power minus 2, okay? Concentration of H positive is 10 raised power minus X, raised power stoichiometric coefficient 4. Now this 10 power minus 2, here 10 power minus 2 gets cancelled out, it becomes 10 raised power minus 4, divided by 10 raised power minus 4x. Okay. Now, since you know the Nernst equation, Nernst equation says that E cell is equal to E naught cell minus 0.0591 divided by N, and it's the log of QC. This is your Nernst equation. Now, as far as the question is concerned, question is saying that if E cell is equal to E naught cell, when can E cell become equal to E naught cell? E cell can become equal to E naught cell if this term becomes 0. E cell will be equal to E naught cell if this entire term becomes 0. When can this entire term become 0? This entire term can become 0 only if QC value becomes 1. Then only log of 1 is 0. So I would say E cell would be equal to E naught cell if QC value is equal to 1. If QC value is equal to 1. Right? If QC value is equal to 1. QC we already got. How much is that? That is 10 raised power minus 4 divided by 10 raised power minus 4x. This value has to be equal to 1. It means that 10 raised power minus 4 is equal to 10 raised power minus 4x. So when you compare, x value is nothing but 1. So this is something I was supposed to calculate. Right? Perfect. All right, so this was how to write the Nernst equation for the complete cells. Now, before discussing the Nernst equation at equilibrium, a small 15 minutes break I'm taking. So, you guys also take it because a lot of students had been asking about the break. So, break I'll be giving till 10:45. But everyone be back because this is again one of the very important topics that has to be covered. Okay? All right. See you after the break, guys. See you after the break. Guys, can you hear me? Can you all hear me? Am I audible, visible to everyone again? What's happening in the chats? Do you want me to block all of you? All right. Fazan, I've done engineering. I'm BTech Civil. Okay. Let's move on now. So now we are going to talk about the Nernst equation at equilibrium. This again one important topic and simple too. Perfect, but have a proper attention on the screen now so that you understand what is meant by the Nernst equation at equilibrium. So first of all, people, let's say I am again taking a Daniell cell here. I hope you remember your Daniell cell. And in case of Daniell cell, how many electrodes do we use? We use 2 electrodes. What all electrodes are used in Daniell cell? The first electrode is going to be your zinc electrode. Let's say this is your zinc rod, which is introduced in zinc sulfate solution. And similarly here, I'm introducing a copper rod in what? In copper sulfate solution. So I have taken 2 electrodes. One is your zinc electrode and one is your copper electrode. Now, my dear students, again, I'm connecting them externally as well as internally with the help of a salt bridge. Again, I'm connecting them externally as well as internally with the help of what? With the help of salt bridge. Now, my dear students, you know, at anode what happens? Oxidation. At cathode what happens? Reduction. This is your anode first of all, at which oxidation is going to take place. And this is your cathode, at which a reduction is going to take place. If you remember, one thing I've already discussed with all of you. What is that? I've told you a reduction potential of an electrode is directly proportional to the concentration of electrolyte present in the container. A reduction potential of the half cell, a reduction potential of the electrode is directly proportional to what? It is directly proportional to the concentration of electrolyte present in the container. More the concentration of electrolyte in the container, more is going to be the reduction potential of the electrode. As simple as that. More the concentration of electrolyte in the container, more is going to be the reduction potential of the electrode. Now try to understand what exactly I'm going to say. My dear students, when this cell will start working, at anode oxidation is going to take place. The zinc atoms from the rod, they are going to get converted into zinc dipositives. And those zinc dipositives will enter into this solution. And as soon as zinc dipositive enters into this solution, from the salt bridge SO4 dinegative will come and will neutralize it. So zinc dipositive coming from the rod, entering into the solution, SO4 dinegative coming from here. So what does that mean? That means in this container, the concentration of ions, the number of ions are increasing. That means in this container, in this anodic container, the number of ions, the concentration of ions is increasing. Or in other words, I can say the concentration of zinc sulfate in this left container, it increases with time. It increases with time, right? Similarly, Cu dipositives, they collide with the rod. Cu dipositives, which are in this solution, they collide with the rod. They get converted into copper solid. That copper solid gets deposited on the rod. That copper solid gets deposited on the rod. So I would say the number of ions in this solution, they decrease with time. Or I can say concentration of copper sulfate, it decreases with time. Now, since if the concentration of zinc sulfate is increasing, that means if the concentration of zinc sulfate, if the concentration of electrolyte in this container is increasing, that means the reduction potential of this electrode is increasing. So with time, the reduction potential of this electrode will keep on increasing. Similarly, if the concentration of electrolyte in the right container decreases, that means the reduction potential of this electrode, this copper electrode, it decreases with time. So on one side, I would say reduction potential of zinc electrode is increasing. On other side, reduction potential of copper electrode is decreasing. Can I say there will be a time when the reduction potential of both the electrodes will be equal? There will be a time when the reduction potential of both the electrodes will be equal. At that point of time, there will be no potential difference between these electrodes. There will be zero potential difference. And when there will be zero potential difference between the electrodes, the current will stop. The current will not be produced from the cell. And that stage in the cell is called as the equilibrium stage. That stage in the cell is called as the equilibrium stage. So in short, as this cell keeps on working, the concentration of zinc sulfate in this container will keep on increasing. That means the reduction potential of this electrode, this zinc electrode, will keep on increasing. The concentration of copper sulfate decreases with time. So reduction potential of copper electrode decreases with time. On one side, reduction potential of zinc electrode increases. On other side, reduction potential of copper electrode decreases. There will be a time when the reduction potential of both the electrodes will be equal. At that point of time, there will be zero potential difference between these electrodes. And at that point of time, the cell will stop working. And that stage in the cell is called as equilibrium stage. So I must say, in short, at equilibrium, the potential difference between the electrodes, that is equal to zero. The potential difference between the electrodes is equal to zero, right? Now, if E cell is equal to zero, since you know delta G is equal to minus NF E cell, delta G is equal to minus NF E cell. If E cell is equal to zero, that means delta G also will be equal to zero. So these are the first two important things which you have to remember. When equilibrium is established in the cell, at that point of time, E cell as well as delta G for the cell, it becomes zero, right? Right, people? I believe this is clear till here. Now, if you write the Nernst equation, the actual Nernst equation, that was E cell is equal to E naught cell minus 2.303 RT divided by NF, it used to be log of QC. This used to be my actual Nernst equation. Now, if I write this Nernst equation at equilibrium, if I write the same Nernst equation at equilibrium, then instead of E cell is equal to 0. This E naught cell comes on this side, so minus E naught cell, minus minus gets cancelled out. So the equation becomes E naught cell is equal to 2.303 RT divided by NF log of. At equilibrium, we do not write QC. At equilibrium, QC is replaced by AEQ. At equilibrium, reaction quotient is called as the equilibrium constant. At equilibrium, reaction quotient is called as the equilibrium constant. So first of all, this particular result is valid when equilibrium will be established in the cell. Okay. Now, if you put the value of R, as 8.314 joules per Kelvin per mole, if you keep the temperature as 25 degrees centigrade, that means 298 Kelvin. If you take the Faraday's constant exactly as 96500 Coulomb, if you put all these parameters into this equation, the equation further reduces like this. E naught cell is equal to 0.0591 divided by N, and then it becomes log of KEQ. Okay. This is the simplified form of the Nernst equation at equilibrium. I believe this is clear. And my dear students, if this is clear, there is one more result which I would want to show you over here. What is that result? Let's have a look. Since the equation from where I have derived the Nernst equation, that was delta G is equal to delta G naught plus RT ln of QC. This used to be the main equation. Now, people, if I write the same equation at equilibrium, at equilibrium, your delta G is 0. And as I told you, QC is replaced by KEQ. So put these in this particular equation. What you'll be getting? You'll be getting delta G naught is equal to minus RT ln of KEQ. Or you can write delta G naught is equal to minus 2.303 RT log of KEQ. Log of KEQ. So these two results are again important from which questions can be framed. I believe it's clear to everyone. I believe it's clear to everyone. Okay? So when equilibrium is established in the cell, when the cell attains equilibrium, what happens exactly? You know it now? You know it now, guys, quick. When equilibrium is established in the cell, at that point of time, E cell becomes 0, your delta G also becomes 0, right? And I believe you know how it happens. Now let's see what kind of questions can be framed from this Nernst equation at equilibrium. The first and the simplest question, which you have on your screen. You are given with the cell reaction, E naught is given, we have to calculate equilibrium constant. We have to calculate equilibrium constant. Now people, pretty much simple. Since we have to calculate the equilibrium constant, so I believe the cell is at equilibrium, and at equilibrium E naught cell is equal to 0.0591 divided by N, and it's log of KEQ. Correct? What is the N value for the reaction? As you can see, zinc is losing 2 electrons and cadmium dipositive is gaining those 2 electrons. So N value is given to me as 2. E naught is given as 0.46. So this becomes 0.0591 divided by N value is how much? 2 log of KEQ. So when you cross multiple, you get a log of KEQ as 15.6, or I would say KEQ is equal to NT log of 15.6. And how do you calculate NT log of 15.6? A simple trick is there. 15.6 you can break as 15 plus 0.6. Okay, you can break it as 15 plus 0.6. This 15 you can directly write as 10 raised power 15 multiplied by this 0.6. 0.6 is basically log of 4. So it becomes 4 into 10 raised power 15. So this is the value of equilibrium constant which I was supposed to calculate. Yeah? I believe this is clear to everyone. Now, for example, look at this question. Look at this question, guys. Look at this question. We are given the reaction, as you can see in this particular reaction, N value is equal to 2. Okay? Equilibrium constant is given. We just need to calculate E naught cell. So just simple E naught cell is equal to 0.0591 divided by N value is 2 log of KEQ. KEQ is given to me as 10 raised power 6. Just one step question this is. Log of M raised power N is N log M. So 6 comes to the front, log 10 is 1. So it is 0.0591 multiplied by 3. This is the E naught cell, which I was supposed to calculate in volts. Right? Perfect. Similar sort of question, guys. For a cell involving 1 electron. Cell involving 1 electron means N is equal to 1. Okay. E naught cell is also given. How much? 0.59 volt. What do we have to calculate? Equilibrium constant KEQ. Now, in order to calculate equilibrium constant, I believe the cell is at equilibrium. And when the cell is at equilibrium, the equation which I'll be using, that is E naught cell is equal to 0.0591 divided by N, and it's a log of KEQ. Now, E naught cell is how much? 0.59, right? Is equal to 0.0591 divided by N value is 1. And this is log of KEQ. This is 1 times, this is 10 times. So I would say log of KEQ is equal to 10, right? Or I would say KEQ is equal to NT log of 10. And NT log of 10 is nothing but it will be 10 raised power 10 directly. It is basically 10.0, right? So it will be directly 10 raised power 10. This is the equilibrium constant which I was supposed to calculate. I hope this is like very much clear to all of you. Perfect. Now, my dear students, there comes one more important topic. What is that? That is concentration cells. This is one more important topic. Okay, concentration cells. So first of all, what are these concentration cells? My dear students, if I ask you, till now, whatever galvanic cells you have seen, did we use two same electrodes or two different electrodes? Whatever galvanic cells we have seen till now, did we use two same electrodes or two different electrodes? We used two different electrodes. But in case of concentration cell, what we are going to do? We are going to use two same electrodes. Two same electrodes are used. Okay? Two same electrodes are used. Number one. Number two, E0 cell, in case of the concentration cell, will be 0. Let's try to understand this. For example, here I am taking zinc sulfate, and this is your zinc rod. Zinc rod introduced in zinc sulfate. Here also I am taking zinc sulfate, and you are introducing a zinc rod. So do we have two same electrodes or two different? I've got two same electrodes. If I connect them externally as well as internally, what do I get? When I connect them externally and internally, I'll be getting a complete galvanic cell. Now, if I want to calculate E0 cell, E0 cell is going to be E0 cathode minus E0 anode. What is E0 cathode? Out of these two, one will be cathode, one will be anode. So E0 cathode means SRP of cathode. SRP of cathode means SRP of zinc, minus E0 anode is again SRP of anode. SRP of anode is SRP of zinc. Now SRP of zinc is SRP of zinc minus SRP of zinc. This will come out to be 0. So whenever you have got a complete cell in which two same electrodes are used, the first point that should come into your mind, that is E0 cell. Their E0 cell will be 0. So in case of the concentration cells wherein two same electrodes are used, remember E0 cell value is equal to 0. E0 cell value is equal to 0. Now guys, how this works and all, for that I have to classify this concentration cell into two types. The concentration cell is basically of two types, which we have to discuss. What are the two types of the concentration cells? The first concentration cell would be called as electrolytic concentration cell. Electrolytic concentration cell. And the second one would be called as electrode concentration cell. Electrode concentration cell. What happens in electrolytic concentration cell? Let me first of all tell you, I'll explain this in some time. First of all, take a note of these points. In case of electrolytic concentration cell, concentration of the electrolytes is kept different, but the partial pressure of the electrodes is kept same. Concentration is kept different, partial pressure same. In case of electrode concentration cells, I must say, concentration is kept same, concentration of electrolytes is kept same, but partial pressure is kept different. Now, let's try to understand them one by one. Let's try to understand them one by one. Okay? So first of all, we'll be talking about the electrolytic concentration cell. First of all, we'll be talking about the electrolytic concentration cell. Electrolytic concentration cell. Let me first of all try to make this electrolytic concentration cell. As I told you already, in case of electrolytic concentration cell, what happens? Just a second. Just a second, guys. Just give me a second, okay? Just give me a second. Okay. In case of electrolytic concentration cells, the first point which I'm going to write here, EMF is generated. EMF is generated due to the difference in the concentrations of the electrolytes. Try to understand what it means. Try to understand what it means. See, guys. For example, this is one of the containers which I've taken, and this is one more container. Okay, two containers I have. Let's say here in this particular container, we have got Mn positive ions. In this container also, we have got Mn positive ions. Okay, let's say the concentration of Mn positive in this container is equal to C1 molar. The concentration of Mn positive in this container is, for example, C2 molar. Now, for example, you are introducing a metal rod M in this container. And in this particular container also, you are introducing a metal rod M. So how many electrodes do you see? 2 electrodes. You can see 2 electrodes. Now connect them externally and internally. Connected them externally. Connected them internally as well. Okay. So in this particular cell, do you see 2 same electrodes used? Yes. So it is the concentration cell in which 2 same electrodes are used. Now, are the concentrations kept same or different? Concentrations are kept different. So it is the electrolytic concentration cell. How do I represent it first of all? See guys, in the middle, I'll be using 2 lines which represent your salt bridge. On the left side, I'll be writing anode, and at anode, your M solid will be getting converted into Mn positive. At anode, M solid gets converted into Mn positive aqueous, whose concentration is kept as C1 molar. On the right side, we have got cathode, and at cathode, reduction takes place. Mn positive gets converted into M. At cathode, Mn positive aqueous, which was there in the right container, whose concentration was C2 molar, it got converted into M solid. So first of all, you have represented this particular cell. You have represented this particular cell. So first of all, the point is, when will this cell work? What condition this cell has to follow so that it will work? The condition is pretty much simple. For any galvanic cell to be working, its cell reactions must be spontaneous. That means at anode, oxidation should take place, and at cathode, reduction should take place. Okay? At anode, oxidation should take place. M should get converted into Mn positive. I would say M solid should get converted into Mn positive aqueous. With that, you'll be writing N electrons. Okay, and its concentration is nothing but C1 molar. What should be the reaction taking place at cathode? For the cell to be working, at cathode, a reduction should happen. Mn positive should get converted into M. So I would say Mn positive aqueous, whose concentration is C2 molar, I would say it should gain some N electrons and get converted into M solid. Okay. So in both the reactions, the electrons are already balanced. If the electrons are balanced, let me directly add these 2 reactions. And when you add these 2 reactions, what will happen? This N and this N will get cancelled. This M solid will get cancelled. So my net reaction is going to be Mn positive aqueous gives Mn positive aqueous. But their concentration is different. The concentration of this is C2 molar and the concentration of this one is C1 molar. Now, if I ask you, what should be the reaction quotient? Reaction quotient should be C1 divided by C2. C1 divided by C2. Okay. If I ask you what should be the E0 cell value, since 2 same electrodes have been used, so E0 cell will be 0. E0 cell will be 0. Now, my dear students, just try to understand one thing. If I write the Nernst equation says that E cell is equal to E naught cell, that is 0, minus 0.0591 divided by N, and it's log of QC. QC is how much? QC is C1 divided by C2. Or I can write it like this. E cell is equal to 0.0591 divided by N. Multiply this log with minus, it becomes log of C2 by C1. Log of C2 divided by C1. Correct? This is your E cell expression. If this is your E cell expression, now we can easily form the condition. We can easily form the condition for this cell to be working. The condition would be, I would say, for the cell, for the electrolytic concentration cell, for the electrolytic concentration cell to be working, okay, by the way, which electrolytic concentration cell is this? For the electrolytic concentration cell, I would say involving metal ion electrodes. Involving metal ion electrodes. For the electrolytic concentration cell involving metal ion electrodes to be working like a normal galvanic cell. Like a normal galvanic cell, I would say delta G should be negative, or I can say E cell should be positive. Or I can say E cell should be positive. You know that already. For any galvanic cell to be working, right, its cell reactions must be spontaneous. Cell reaction must be spontaneous means delta G should be negative. And if delta G is negative, that means its E cell should be positive. We have discussed this. Now the point is, when can this E cell be positive? This E cell can be positive only if this entire term is positive. When can be this entire term positive? Entire term is positive only if log of C2 by C1 will be positive. Now when is log of X positive? Log of X is positive only. Log of X is positive only when X will be greater than 1. I would say when C2 divided by C1 would be greater than 1, which tells you that C2 has to be greater than C1. Now what is C2 and what was C1? C2 is the concentration of electrolyte in cathode. C1 is the concentration of electrolyte in anode. So I would say concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode. Then only EMF of the cell will come out to be positive. And once EMF of the cell comes out to be positive, then only delta G will come out to be negative. Then only cell reactions will be spontaneous. Then only at anode oxidation will happen, at cathode reduction will happen. Electrons will move from anode to cathode and current will move from cathode to anode. So this is the condition, my dear students, which this cell has to follow. Then only its cell reactions will be spontaneous. Otherwise not. Right? Am I clear with this point? Is this particular point clear? Perfect, guys. Now there is one more thing here in this electrolytic concentration cell. Understand that also. I'm marking the heading as electrolytic concentration cell involving hydrogen electrodes. Electrolytic concentration cell involving hydrogen electrodes. See how this cell looks like first of all. Duration of this particular session, I'll just take 1 more hour. Okay? I'll just take 1 more hour. Sir, did you work in Chennai with Shimon, sir? Me and Shimon, we started our teaching career together from Chennai, yes. Yes. Right. Back in 2018, we started. Both of us. And he's a very good friend of mine. All right. Electrolytic concentration cell involving hydrogen electrodes. Let's have a look on this now as well. First of all, how this particular cell looks like. See guys, in the middle, I'm keeping two lines which represent your salt bridge. On the left side of the salt bridge, what do we have? We have got anode, right? Let's say your anode is like this. H2 gas, H positive aqueous. Let's say the pressure of H2 gas is P bar and concentration of H positive aqueous is, for example, C1 molar. And here I'm using platinum solid. So the anode is my hydrogen electrode. Anode is my hydrogen electrode. Now, if you want to have a look on the cathode is again the hydrogen electrode only. H positive aqueous, this is H2 gas. Let the concentration of H positive in the cathodic container is C2 molar. Let the pressure of this is P bar only. And this is platinum solid. This particular cell, look at this particular cell. Look at this particular cell carefully, guys. Two same electrodes are used. The pressure is kept same, but the concentration is different. So this is electrolytic concentration cell. Involving which electrodes? Involving hydrogen electrodes. Now, what is the condition? What is the condition for this particular cell to be working? We have to frame that condition. We have to make that condition. To make that condition, I must say, for this cell to be working, its cell reactions must be spontaneous. And when can be its cell reaction spontaneous? What is meant by that term? Its cell reaction must be spontaneous. That means at anode, oxidation should happen. At cathode, reduction should happen. So at anode, I must say, your H2 gas should get converted into H positives. And with that, you'll be writing 2 electrons. What was the pressure of this H2 gas? It was P bar. What was the concentration of H positive? It was C1 molar. Similarly, reaction at cathode. At cathode, reduction should happen. H positive should get converted into H2. So the reaction has to be 2 times H positive aqueous, whose concentration is C2 molar. It should be gaining 2 electrons and getting converted into H2 gas, whose pressure is again P bar. Whose pressure is again P bar. Now tell me one thing. Are the electrons balanced in both? In both the reactions, the electrons are balanced. And since the electrons are balanced, so you can cancel them up and value will come out to be 2. Right? What all things will get cancelled? This H2 gets cancelled because their pressure is same. So my net reaction becomes 2 times H positive aqueous, whose concentration is C2 molar. It gives 2 times H positive aqueous, whose concentration is C1 molar. Now, if I would want to write the expression for QC, it becomes C1 square divided by C2 square. So I will write C1 by C2 whole square. Or let me write it directly. What was C1? C1 is the concentration of H positive in anodic container. So this is the concentration of H positive in anode divided by what is C2? C2 is the concentration of H positive in cathode. Whole raised power what? Whole raised power 2. Again, if I ask you what about the E0 cell value? Since it's the concentration cell wherein 2 same electrodes are used, so E0 cell has to be 0. E0 cell has to be 0. Now, my dear students, as per your Nernst equation, E cell will be equal to E0 cell is 0 minus 0.0591 divided by n value is how much? 2 log of QC. How much is QC? QC is concentration of H positive in anode divided by concentration of H positive in cathode whole raised power 2. E cell is equal minus 0.0591 divided by 2 log of m raised power n is n log m, so 2 comes to the front. So this becomes a log of m by n. Log of m by n is nothing but log of m minus, or let me just write it like this, yeah, minus log of n. Okay, so this 2 gets cancelled. E cell will be equal to 0.0591. Okay, 0.0591. Now, take this minus inside. It becomes minus log of H positive in anode minus times minus log of H positive in cathode. Minus log of H positive in cathode. Perfect. So my net equation becomes E cell is equal to 0.0591 minus log of H positive anode means pH of anode minus log of H positive means pH of cathode. So this is my final equation to calculate EMF of the electrolytic concentration cell involving hydrogen electrodes. Now for this cell to be working, I must say, for this cell to be working like a normal galvanic cell, what should be the condition? The condition is pretty much simple. For this cell to be working, again, delta G should be negative, then only cell reaction will be spontaneous. Delta G negative, that means E cell should be positive. How E cell will be positive? E cell will be positive only if pH of anode would be greater than that of pH of cathode. If pH of anode is greater than pH of cathode, then only this entire term will come out to be positive. And once E cell is positive, automatically delta G becomes negative. And once delta G is negative, cell reactions will be spontaneous. And cell reaction spontaneous means electrons will move from anode to cathode, current will flow from cathode to anode. That's all. Yeah? Right, people? Is this particular point clear? So, for the electrolytic concentration cell involving hydrogen electrodes to be working like a normal galvanic cell, pH of anode should be greater than that of pH of cathode. Let me first of all see whether you will be able to solve some questions or not. Take this particular question. What do you think about this one? What do you think about this particular question? Do you see two same electrodes? Yes. So it's a concentration cell. Is the concentration same or different? Concentration is different. So it is the electrolytic concentration cell. Right? It's the electrolytic concentration cell. Now, for the electrolytic concentration cell involving metal ion electrodes to be working, concentration of cathode should be greater than concentration of anode. Concentration of electrolyte in cathode. What is the concentration of electrolyte in cathode here? C1. Right? So this cell will work only if C1 is greater than C2. This is the condition for the cell reactions to be spontaneous. This is the condition for the cell reactions to be spontaneous. Correct? We have discussed it a few minutes back only. Now the question is, the cell reactions will be spontaneous if C1 is greater than C2. If C1 is greater than C2, cell reactions are spontaneous. Yes, correct. If C2 is greater than C1, anodic concentration is greater than cathodic concentration, current will flow from cathode to anode. There will be no current. If C1 is greater than C2, if concentration of electrolyte in cathode is greater than that of concentration of electrolyte in anode, cell reactions will be spontaneous. That means electrons will move from anode to cathode. Current will move from cathode to anode. Current will flow from cathode to anode. This is correct. Okay. If C1 is equal to C2, if the concentration of both the electrodes is same, if C1 and C2 are same, this becomes 1. Log of 1 is 0. That means E cell comes out to be 0. And E cell comes out to be 0 means the cell does not work. E cell 0 means the cell does not work. No current is produced. So this is also correct. So A, C and D is the correct answer of the question. Clear? And if this is clear, can you check this particular question out? Just a second, not this one. Yeah, this one also you can check. This one also you can check. If you look carefully, do we have two same electrodes? This is hydrogen, this is hydrogen. Yes, two same electrodes. Pressure is same, concentration is different. So it is the electrolytic concentration cell involving hydrogen electrode. Yeah? This is the electrolytic concentration cell involving hydrogen electrode. How do you calculate its E cell? Few minutes back only I gave you the formula. To calculate EMF of the electrolytic concentration cell involving hydrogen electrodes, E cell is equal to 0.0591 multiplied by pH of anode minus pH of cathode. So I have to calculate pH of anode and I have to calculate pH of cathode. So pH of anode will be what? See, in the anodic container we have got H2SO4. If I talk about your anode, in the anodic container we have got H2SO4. How this H2SO4 would have dissociated? Twice H positive aqueous plus SO4 dinegative aqueous. What is the concentration of H2SO4 which we have taken? 0.05 molar. This would be 0. This would be 0. Now, H2SO4. It's a strong acid, completely dissociated, so this will be 0. 1 mole gives 2. So 0.05 gives 2 into 0.05, which comes out to be 0.1 molar. So I would say, in the anodic container, the concentration of H positive is 0.1 molar. Concentration of H positive in the anodic container is 0.1 molar, which is 10 raised per minus 1. So I would say pH of anode will be simply equal to minus log of H positive concentration of anode. So it's going to be minus log of 10 raised per minus 1. The value comes out to be 1. Okay, so this is the pH of anode. This is the pH of anode. Similarly, look at the cathodic container. In cathodic container, you have taken HCl. In your cathode, we have taken HCl. So HCl would have dissociated as H positive plus Cl negative. Initially, the concentration of HCl is kept as 10 raised power minus 3 molar. So this would be 0, this would be 0. Now this would be 0. This would be 10 power minus 3. So concentration of H positive in the cathodic container. Concentration of H positive in the cathodic container is equal to 10 raised power minus 3 molar. So I would say pH of cathode will be simply minus log of H positive concentration in cathode. So it is minus log of 10 raised power minus 3. The value comes out to be 3. So you got pH of anode as well as pH of cathode. Now your E cell is equal to 0.0591 multiplied by, what is pH of anode? 1 minus what is pH of cathode? That is 3. The value will come out to be positive or negative. The value will come out to be negative. And when E cell comes out to be negative, that means delta G will be positive. And if delta G is positive, the cell reactions will be non-spontaneous. When delta G is positive, the cell reactions will be non-spontaneous. So the cell will not work. That's something I was supposed to check, right? That is something I was supposed to check. I believe this is also clear to every one of you. Yeah? Okay, one more concentration cell is there, my dear students. Let me make you clear with that as well. Or before doing that, look at this question. Two line salt bridge, on the left side hydrogen electrode, on the right side hydrogen electrode. Pressure is same, concentration is different. So it is again electrolytic concentration cell involving hydrogen electrodes. It is again electrolytic concentration cell involving hydrogen electrodes. So its E cell is 0.0591. This is pH of anode minus pH of cathode. Simple. E cell is given to me as 0.2364 is equal to 0.0591. What is the pH of anode? On the left side, you have got anode, so pH of anode is X minus. What would be the pH of cathode? In the cathodic container, H positive concentration is 1. This is the H positive concentration in cathode. So minus log of 1 is 0. So when you solve, X value will approximately come out to be 4. What was this X? X was the pH of the anodic container. So pH of anodic container is coming out to be 4. That's all. Yeah? Perfectly done. Okay, there is one more concentration cell which you have to be familiar with. What is that? What you call as electrode concentration cell. Electrode concentration cell. Now what happens in electrode concentration cell? In electrode concentration cell, let me tell you, EMF is generated. EMF is generated by keeping partial pressure different. EMF is generated by keeping partial pressure different. Let me show it to you exactly. Let me show it to you exactly. For example, this is your salt bridge. On the left side of the salt bridge, you have got anode. Let's say your anode is this H2 gas, whose pressure is, for example, P1 bar. This is H positive aqueous, whose concentration is C molar. Okay, and here I'm writing platinum solid as well. On the right side, I'm using one more electrode, which is again the hydrogen electrode. So H positive aqueous, whose concentration is C molar. This will be H2 gas, whose pressure is P2 bar. Okay, platinum solid. Now, do you see two same electrodes used? Hydrogen, hydrogen. Two same electrodes are used, right? Right, people? I would say in this particular cell, if you see carefully, two same electrodes are used. Now, concentration is kept same. Partial pressure is kept different. That particular concentration cell in which pressure was same, concentration different. That was electrolytic. Here, concentration is same, but partial pressure is different. So this is electrode concentration cell. Okay, this is electrode concentration cell. Well, you can represent this cell in a different way as well. How can you represent it in a different way? See, Do you see H positive whose concentration C? H positive whose concentration C? Instead of this entire term, write only H positive, only one H positive, whose concentration is C. Now on the left side of this H positive, there was H2 gas, whose pressure was P1 bar, right? And this was platinum solid. On the right side of this H2, H positive, there was again H2 gas, whose pressure was P2 bar. And this is platinum solid. Well, you can represent the cell like this as well. There is no need to represent a salt two lines here. You can represent it like this as well. Okay. Instead of this entire part, I just wrote one H positive and the left side of it and the right side of it. That's it. Now, we have to see the condition which the cell has to follow so that its cell reactions will be spontaneous, so that the cell will work. Now, for the cell to be working, for the cell to be working, cell reaction should be spontaneous. Cell reaction spontaneous means at anode, H2 should get converted into, at anode H2 gas, whose pressure is P1 bar, it should get converted into 2 times H positive aqueous, whose concentration is C molar plus 2 electrons. Correct? Now at cathode, H positive gets converted into H2. So I would say 2 times H positive aqueous, whose concentration is C molar, it should gain 2 electrons and get converted into H2 gas. Okay. Now people, electrons are balanced. Okay. Twice H positive will get cancelled out because their concentration is same. This H2 and this H2 won't get cancelled out because their partial pressure is different. One is P1 and one is P2. So my net reaction becomes H2 gas, whose partial pressure is P1 bar. It gives H2 gas, whose partial pressure is P2 bar. Okay. Now, if I ask you, what is the E naught cell value? E naught cell value is 0. You know that already. What is the N value? N value is 2. If you want to write the QC expression is going to be partial pressure of this H2, which is P2, divided by partial pressure of this H2, which is P1. Correct? Which is P1. Now, for this electrode concentration cell to be working, I would say for the electrode concentration cell, which we have right now, to be working like a normal galvanic cell, wherein electrons move from anode to cathode and current flows from cathode to anode. For this cell to be working, its cell reactions must be spontaneous. And cell reactions will be spontaneous only if E cell value will be greater than 0. If E cell value will be greater than 0. Now, first of all, what is the expression of E cell? Expression of E cell is nothing but E cell is equal to E naught cell, which is 0 minus 0.0591 divided by N value is 2 log of QC. QC is P2 by P1. QC is P2 by P1. Or this minus, when you multiply with log, it becomes P1 by P2. This becomes P1 by P2. So for this cell to be working, E cell should be greater than 0. E cell can be only greater than 0 if this term is greater than 0. If log of P1 divided by P2 will be greater than 0. Now, when can be log of x greater than 0? Log of x can be greater than 0 only when x is greater than 1. So, I would say P1 divided by P2 should be greater than 1, which is simply telling you that P1 should be greater than P2. What was P1? What is P2? P1 was the partial pressure of anode. P2 is the partial pressure of cathode. So, I can say partial pressure of anode should be greater than that of partial pressure of cathode. Partial pressure of anode should be greater than the partial pressure of cathode. Then only EMF of the cell will be positive. And once EMF is positive, delta G will automatically be negative. And once delta G is negative, cell reactions will be spontaneous. That means at anode oxidation will happen, at cathode reduction will happen. Electrons will move from anode to cathode and current will flow from cathode to anode. So this is the condition which the cell has to follow. Then only its cell reactions will be spontaneous. Okay? Am I clear with this, people? Quick. Yes, E naught is 0 because of two same electrodes. There is one more topic left in the EMF part, guys. Okay, it is not going to take a lot of time. It is not going to take a lot of time, right? It's a simple topic only. It is thermodynamics of the cell. Thermodynamics of the cell. See, sometimes in the question they'll ask you to calculate delta G for the cell. They'll ask you to calculate delta S for the cell. They'll ask you to calculate delta H for the cell. Gibbs free energy change, right? Entropy change during the cell reaction, enthalpy change during the cell reaction. These can be asked in your examination as well. These three thermodynamic functions. Calculate the Gibbs free energy change, entropy change during the cell reaction, enthalpy change during the cell reaction. Now, how do you calculate delta G for the cell reaction? Similarly, delta S for the cell reaction, delta H for the cell reaction. Let's have a look on that as well. See, one simple thing I'm going to do. I'm going to use one of the equations from the thermodynamics, which is dG is equal to VdP minus SdT. This is one of the equations of the thermodynamics which is used for reversible processes, basically. Reversible processes. Now, my dear students, if I write the same equation at constant pressure, I must say dP value will become 0. If dP is 0, I would say dG is equal to minus SdT. So at constant pressure, dG is equal to minus SdT. Now, for the reactions, you do not define Gibbs free energy. You define change in Gibbs free energy for a reaction. For a reaction, you do not define entropy. You define change in entropy for the reaction. For reactions, entropy change, Gibbs free energy change is defined. So instead of G, you guys are going to write delta G. Instead of S, you guys are going to write delta S. So it becomes D of delta G is equal to minus times delta S for the reaction multiplied by dt. So I would say delta S for the reaction will be equal to minus times D of delta G for the reaction divided by dt, correct? So it becomes minus times D upon dt of delta G. Delta G is nothing but minus NF E cell. Minus NF E cell. Or I can further simplify it a bit. I'll say delta S for the reaction, delta S for the cells, delta S for the cell reaction is equal to minus comes out, NF comes out. So it becomes NF dE divided by dt. Since we had kept pressure constant, so it is at constant pressure. So this is one of the equations by means of which we can calculate entropy change during the cell reactions. When the galvanic cell works, right, entropy change during the reaction is given by this particular formula. And you already know, F you already know, this d by dt is called as temperature coefficient of the cell. This is called as temperature coefficient of the cell. And if I ask you what are going to be its SI unit, this is EMF, this is temperature. So it's volt per Kelvin is going to be its SI unit. Okay. The entropy change units, its SI entropy change unit, SI unit is going to be joules per Kelvin. So this is the formula with the help of which we can calculate delta S for the cell. Similarly, delta G for the cell you already know, that is minus NF E cell. Nothing to do with this particular point. This is something which we already know. Now similarly, how do we calculate delta H for the cell? Since delta G you know, delta S you know, you already have the result. Delta G for the reaction would be equal to delta H minus T delta S for the reaction. What do you have to calculate? I have to calculate delta H for the reaction, which becomes delta G for the reaction plus T times delta S for the reaction. Now, delta G for the reaction is equal to minus NF E cell plus E stands for temperature. Delta S for the reaction we have calculated already, that is NF dE upon dt at constant pressure. Perfect. Now, the final result will be delta H for the reaction will be equal to, if I take NF common, it becomes minus times E cell plus dE upon dt at constant pressure multiplied by temperature. So this is the result with the help of which you can calculate enthalpy change during the cell reaction. So these are the three thermodynamic functions which are asked to us. calculate delta S for during the reaction, during the cell reaction, calculate delta G during the cell reaction, calculate delta H for the cell reaction, right? All the three results are in front of you. Okay. At the same time, sometimes they might ask you about the efficiency of the cell. Sometimes they might ask you about the efficiency of the cell, which is nothing but, which is magnitude of delta G divided by magnitude of delta H multiplied by 100. They might ask you about this as well. Calculate the efficiency of the cell. Delta G divided by delta H multiplied by 100, mod, magnitude. Okay? Right? Now guys, if you look at one more thing, if you want to have a look on variation of EMF, with temperature, how this EMF varies with temperature, how the EMF of the cell varies with temperature. Since we have got two types of cells basically, we have got two types of cells. The first cell whose temperature coefficient d by dt, the first type of the cell whose temperature coefficient is positive, and the second type of the cell whose temperature coefficient would be negative. First type of the cell whose temperature coefficient is positive, second type of the cell whose temperature coefficient is negative. So that particular cell whose temperature coefficient is positive, if you increase the temperature of this cell whose temperature coefficient is positive, if you increase the temperature, I would say dt, change in temperature, will come out to be positive. If dt is positive, that means denominator is positive. The overall term has to be positive. The overall term has to be positive. Denominator is already positive. That means numerator also should be positive. Numerator positive means dE value should be positive. dE positive, what does that mean? dE positive means E2 should be greater than E1. What does that mean? That means on increasing the temperature, EMF increases. On increasing the temperature, EMF increases. So that means EMF of the cell is directly proportional to temperature. But this is not valid for all the cells. This is valid for only those cells whose temperature coefficient is positive. Right? This is valid for only those cells whose temperature coefficient is positive. Correct? Similarly, what about those cells whose temperature coefficient is negative? When you increase the temperature of such cells whose temperature coefficient is negative, when you increase the temperature, that means dt value will be positive. dt is positive. Overall term has to be negative. That means numerator has to be negative. Numerator negative means dE value is equal to negative. When is dE negative? dE negative means E2 would be less than E1. That means EMF of the cell decreases. That means EMF of the cell decreases. So EMF and temperature, are they now directly proportional or inversely? They are inversely proportional to temperature. But this particular thing is valid for only that particular cell whose temperature coefficient would be negative. Okay? Whose temperature coefficient would be negative. So EMF and temperature, they are related, they are directly proportional as well as inversely proportional, depending on whether the temperature coefficient of the cell is positive or the temperature coefficient of the cell is negative. Correct? One question with that will end the session. Okay? Look at this particular question. We are given with a reaction. Look at the reaction. N value is equal to 2. N value is equal to 2. What all things we have to calculate? Delta G, delta H, delta S. See, delta G is nothing but, that is minus NF E cell. Simple. N value is 2. F is 96500. And E cell is given to me in the question, which is 1.018. When you solve this, the answer will be in joules. Similarly, delta S. Delta S will be minus times NF d by dt at constant pressure. Was it minus times or plus? I think it was NF d by dt. It was not minus. It was NF d by dt. So, N value, you know already, that's 2. F value is 96500. d by dt is called as temperature coefficient. That's given to me. That is minus 5 into 10 raised power minus 5. Since all the parameters are used as per SI system, so delta S will come as per SI system, which is going to be joules per Kelvin. Similarly, your delta H. Delta H formula a few minutes back we made. NF, this is minus E cell, plus dE upon dt at constant pressure. multiplied by temperature. So N value is 2, F is 96500, minus E cell 1.018, plus dE by dt is how much? Minus 5 into 10 raised power minus 5. And temperature in Kelvin will be, I think something is, okay, temperature in Kelvin will be 298 Kelvin. Again, the matter of calculation, you'll be getting the delta H, that too in joules. Okay? And my dear students, with this, the EMF part of this particular chapter is over. There is one more part left in this chapter, that is electrolysis part. As I've told you, I will break this chapter into 2 parts. This was part 1, and part 2 I'll be posting tomorrow morning. That will be 3 to 4 hour session. Okay? That will be the recorded part, but that will be the recorded session. All right? That would be the recorded session. So are all the things clear till here? Everyone wants? Did you understand it properly? Whatever things I have discussed with all of you? So with this, your EMF part of electrochemistry chapter, that means 70% of the chapter is done. The remaining 30%, I'll be providing you in the morning exactly at 10 a.m. Right? That will be a 3 to 4 hour session, a recorded session. Okay? That will be also detailed. So tomorrow by 1 or 2, you'll be done with this particular chapter. All right? Perfect. And do let me know in the comment section of this particular video, which chapter do you want the next? Okay? Do let me know in the comment section of the video. I would want you guys to write in the comment section which chapter do you want me to take next. And at the same time, one more thing. On Saturday, I'll be taking the session. On Saturday. But you are going to let me know in the comment section. Okay? Chalo. With this, I'll be taking leave. I wanted to take the 4-hour session live, the part 2 of this chapter, but tomorrow it's Ambika ma'am session. Okay? Tomorrow it's Ambika ma'am session, so I cannot, the whole schedule will get altered. It's one and the same thing. It's one and the same thing, don't worry. Okay. Anyways, the PDF of this session, wherein I had already kept the electrolysis part also, you'll be getting this PDF in the Telegram. Okay, you would be getting the PDF of this in the Telegram. All right. This PDF I'll be sharing in the Telegram. Hello guys. Thank you so much. See you. Bye-bye.